Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the cold precision of infrared astronomy and the strange chemistry of an object that came from somewhere else entirely. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The James Webb Space Telescope hangs in darkness at Lagrange Point 2, 1.5 million kilometers from Earth, where the gravitational influences of planet and sun balance into stillness. Its 18 gold-plated beryllium mirrors, each polished to within 10 nanometers of perfection, collect photons that have travelled impossible distances. The telescope does not see the way human eyes see. It observes in the infrared, wavelengths longer than red, invisible to organic vision, the spectrum where cold things glow and distant things whisper. The gold coating, just 100 nanometers thick, reflects these longer wavelengths with exceptional efficiency, a choice of material dictated by physics rather than aesthetics, though the result happens to be beautiful in the wavelengths humans can perceive. In December, the telescope's sensors register a new source. Not a galaxy, not a nebula, not the fossil light of the early universe that Webb was primarily designed to study, something closer, something moving. The object appears first as a cluster of pixels slightly brighter than the background noise, a pattern the software flags for human attention. Within hours, astronomers confirm what the preliminary orbital calculations suggest. This is not bound to the Sun. Its velocity, its trajectory, the shape of its path through space, all the mathematics point outward, away, toward the permanent exile of interstellar distance. They designate it 3Y/Atlas. The 3I means third confirmed interstellar object. The Atlas comes from the ground-based survey in Hawaii that first detected it, the Asteroid Terrestrial Impact Last Alert System, 4 telescopes scanning the night sky for anything that moves against the fixed stars. Before Webb's more sensitive instruments began their observations, Atlas caught the visitor as a faint smudge migrating across the constellation background, notable only because its motion suggested something unusual about its origin. Already the object is retreating, falling back toward the outer solar system and then beyond, toward the heliopause where the sun's influence fades into the vast nothing between stars. Already the window for detailed study is closing, measured in weeks rather than months, a cosmic opportunity that will not repeat within any human lifetime. Webb turns its mirrors toward the visitor. The telescope's mid-infrared instrument, called MIRI, cools itself to 7 degrees above absolute zero, cold enough that its own thermal radiation does not overwhelm the faint signals it seeks. The cooling system relies on a cryocooler, a mechanical refrigerator that operates continuously in the vacuum of space, compressing and expanding helium gas to extract heat from the instrument's detectors. Without this active cooling, MIRI would see only itself, its own warmth drowning out the faint infrared glow of distant objects. The near-infrared spectrograph, NIRSpec, splits incoming light into its component wavelengths, transforming photons into data, brightness into chemistry. What the telescope sees, or rather what it measures, is not an image in any familiar sense but a spectrum, a graph showing how much light arrives at each specific wavelength, each frequency, each colour that human eyes cannot perceive. The spectrum contains surprises. Lines and bands appear where planetary scientists do not expect them, emission features that correspond to molecules and atoms that should not be present in these abundances, in these combinations, at these temperatures. The data arrives at the Space Telescope Science Institute in Baltimore, Maryland, where astronomers begin the slow work of interpretation, cross-referencing the observed wavelengths against laboratory measurements of known compounds, comparing the intensities to models of cometary outgassing and dust grain composition. Some features match known molecules: water, carbon dioxide, carbon monoxide, the usual suspects in cometary spectroscopy, but other features do not match anything in the standard libraries of spectral signatures. December light falls cold on Earth. The telescope, hanging in its engineered void, observes without cold, without warmth, without any sensation at all. It measures photons. It counts arrivals. The mirrors collect. The sensors record. The spacecraft transmits data back toward the pale blue dot that built it. And in that transmission, in that cascade of bits travelling at light speed across the vacuum, travels evidence of worlds no human instrument has visited, chemistries no solar system body displays, histories written in atomic abundance ratios and molecular complexity. Each photon that strikes the detector array liberates an electron in the silicon substrate. A tiny pulse of current amplified and digitized, converted into numbers that will be analysed by computers and minds separated from the light source by distances measured in parsecs. The object itself, the actual physical thing, whatever it is, remains impossibly far away. Even at its closest approach to the Sun, 3I/Atlas stays beyond Mars's orbit, hundreds of millions of kilometres distant. Webb cannot resolve surface features. The comet, if it is a comet, appears as an unresolved point source surrounded by a diffuse coma of gas and dust, the characteristic signature of volatiles sublimating in sunlight after eons of frozen darkness. But the chemistry of that coma, the specific compounds evaporating into space, the ratios of elements and isotopes, these tell stories that ground-based telescopes, peering through Earth's obscuring atmosphere, cannot fully read. The atmosphere absorbs most infrared wavelengths, blocks the very light that carries the clearest chemical signatures, which is why Webb had to be placed beyond the sky, in the perfect darkness where nothing interferes with observation except the faint zodiacal light of dust grains orbiting the Sun. Only took 4 billion years to build instruments capable of this measurement, only required the collective technological development of an entire species, the refinement of mirror polishing techniques to atomic precision, the invention of cryogenic cooling systems and infrared-sensitive detector arrays, the construction of rockets powerful enough to place 6 metric tons of delicate instrumentation beyond Earth's gravitational well, the establishment of a global network of radio telescopes to receive the faint signals from the spacecraft's transmitter, only needed all of human history. Really, to reach the point where a mind on one planet can analyse the chemistry of an object from another star system. The telescope itself represents 30 years of planning and construction, multiple redesigns, budget negotiations, international collaboration, the careful choreography of hundreds of engineering teams working to tolerances that leave no room for error, and now it works, suspended in the void, observing strangers. The telescope observes, the data accumulates. The light that left 3I/Atlas milliseconds ago arrives now, captured, measured, stored. Somewhere in the spectrum, encoded in the brightness at specific wavelengths, lies evidence of the object's origin, clues about where it formed, what star it once orbited, what processes shaped its composition before it was ejected into the galactic dark. The astronomers work to extract these clues, to translate photon counts into understanding, to reconstruct a history from the language of light. They compare the spectrum to databases of laboratory measurements, to theoretical models of molecular formation in different temperature and pressure regimes, to observations of comets native to this solar system. They search for patterns, for matches, for explanations. But mysteries remain. Some spectral features resist easy interpretation. Some abundance ratios fall outside the range of any solar system comparison. Some of the chemistry appears, in the cautious language of peer-reviewed papers, anomalous. The words scientists use when they mean, "we don't understand this yet," We need more data, we need better models, we need to revise our assumptions about what is possible. The peer review process moves slowly, carefully, each claim verified before publication, each measurement checked and rechecked, because extraordinary claims require extraordinary evidence. And an interstellar object with impossible chemistry qualifies as extraordinary by any measure. And 3I/Atlas continues its journey outward, oblivious to observation, indifferent to interpretation, following the trajectory that gravity and momentum dictate, receding into darkness at 17 kilometers per second relative to the Sun, carrying its impossible elements back into the interstellar medium from which it emerged. The object does not know it is observed. It does not care about the infrared photons it reflects and emits, the spectral signatures it broadcasts. It simply moves, as it has moved for millions or billions of years, through the empty spaces between stars, occasionally passing near enough to a planetary system to feel the slight tug of gravity, the gentle curve in its trajectory, before continuing onward into regions of space that will never know starlight again. The mathematics of the trajectory tells the story before any chemistry can be analysed. Orbital mechanics reduces motion to equations, curves to numbers, futures and pasts to calculable certainties. When astronomers plot the path of 3I/Atlas through space, when they measure its velocity and direction, when they account for the gravitational influence of the Sun and the planets, the result is unambiguous. This object's orbit is hyperbolic, not elliptical like the paths of planets and asteroids and comets native to this system. Not even parabolic, the boundary case between bound and unbound. Hyperbolic, a trajectory that carries the object past the Sun once and never again, a path that guarantees permanent departure. The eccentricity of the orbit exceeds 1.0. In the language of orbital mechanics, eccentricity measures how stretched an orbit is, how far it deviates from a perfect circle. An eccentricity of 0 describes a circle. Eccentricities between 0 and 1 describe ellipses, the shapes that planets trace around stars, that moons trace around planets, that bound objects follow under gravity's influence. An eccentricity of exactly 1 describes a parabola, the limiting case where an object has precisely enough velocity to escape but no excess. Anything above 1 describes a hyperbola, and anything following a hyperbolic path around the Sun is not from here. 3I/Atlas has an eccentricity of approximately 3.2. The number means the object arrived from interstellar space with considerable excess velocity, speed beyond what solar gravity could capture, momentum inherited from whatever stellar encounter ejected it from its birth system millions or billions of years ago. The mathematics allows no other interpretation. This is not a long-period comet from the Oort cloud, not a Kuiper belt object perturbed inward, not anything that ever belonged to the Sun's gravitational family. It came from outside, and it will return outside. And the sunlight warming its surface now is a temporary anomaly in an existence spent almost entirely in the cold dark between stars. Astronomers can calculate the object's past positions, tracing the trajectory backward through time. 1 year ago, 3I/Atlas was farther from the Sun, colder, inactive, undetectable by ground-based surveys. 10 years ago, it was crossing the outer solar system past Neptune's orbit, still approaching. 100 years ago, it was beyond the Kuiper belt, moving inward at the same 17 kilometers per second it carries now, unobserved and unobservable, its existence unknown to any mind in the universe. The trajectory, extended backward far enough, points toward a specific region of the sky, not toward any particular star, but toward a general direction, a line of sight that intersects nothing bright, nothing close, nothing that human astronomers have named. The precision of trajectory determination depends on the number and quality of observations. Early measurements, from ground-based telescopes catching brief glimpses through turbulent atmosphere, contained significant uncertainties. The object's position was known only to within thousands of kilometers, its velocity uncertain by meters per second, its future path subject to multiple possible solutions. But as observations accumulated, as more telescopes contributed data points, as Webb's precise measurements refined the positional information, the uncertainties shrank. Now the trajectory is known well enough to predict the object's position decades into the future, centuries even, though by then it will be too faint to see, lost against the background stars. Only took a few weeks of observation to prove the object would never return. Only needed a handful of precise measurements to calculate the eccentricity, to confirm the hyperbolic nature of the path, to eliminate any possibility that this might be a solar system native on an unusual but bound orbit. The mathematics, once solved, admits no ambiguity. Gravity does not negotiate. The object arrived with too much speed, passed too far from the sun's strongest gravitational influence, and will depart with velocity sufficient to reach interstellar space within a few thousand years, a brief interval on cosmic timescales, barely worth noting in the long history of galactic motion. The trajectory also reveals what did not happen. 3I/Atlas did not pass close enough to Jupiter to be captured or significantly deflected. It did not approach any planet within that planet's hill sphere, the region where a world's gravity dominates over the sun's influence. It threaded a path through the solar system that brought it near nothing, touched nothing, disturbed nothing except the photographic plates and sensor arrays that recorded its passage. In a different century, with different timing, the object might have crossed Earth's orbit at the moment Earth occupied that position, might have approached close enough to show detail, structure, surface features. But the timing was not different, and the closest approach to Earth exceeds 1 astronomical unit, 150 million kilometers, far enough that even Webb sees only an unresolved point surrounded by fuzzy coma. The path intersects the plane of the solar system at a steep angle, another signature of external origin. Most objects native to the Sun's family orbit in roughly the same plane. The flat disk inherited from the protoplanetary nebula that collapsed to form the system 4.5 billion years ago. Comets from the Oort cloud can arrive from any direction, but their velocities, when they fall inward toward the Sun, reflect the gravitational acceleration gained from starting at rest in the outer reaches of solar influence. Interstellar objects arrive with their own velocity vectors, directions determined by galactic motion rather than solar system dynamics. And those directions rarely align with the ecliptic plane. 3I/Atlas approaches from above the plane, descends through it near perihelion, and departs below, carving a straight line, or rather, a gentle hyperbolic curve, through the disk of planets and asteroids. The inclination of its orbit, measured relative to Earth's orbital plane, exceeds 40 degrees, not the steepest inclination ever observed. Some long-period comets arrive nearly perpendicular to the ecliptic, but combined with the hyperbolic eccentricity, the steep inclination strengthens the case for interstellar origin, adds another line of evidence to the growing file of proof. Trajectory determination requires accounting for non-gravitational forces, comets, as they sublimate volatiles in sunlight, experience tiny accelerations from the rocket effect of outgassing, jets of vapour pushing against the nucleus, altering the orbit slightly, introducing perturbations that purely gravitational models cannot predict, for 3I/Atlas. These non-gravitational accelerations complicate the trajectory calculations, introduce small uncertainties into long-term predictions. The outgassing is asymmetric, stronger on the sunward side, variable in intensity as different ices reach sublimation temperature at different distances. The effect is subtle but measurable. A few millimeters per second of velocity change accumulated over weeks of observation. Only in the last century has humanity possessed the mathematical and computational tools to solve these problems. Newton gave us the equations of motion, the laws of gravity, the foundation of orbital mechanics. But calculating the trajectory of an object under non-gravitational acceleration, accounting for the gravitational influences of multiple planets, extracting a precise solution from noisy observational data. These tasks require numerical methods, iterative refinement, computational power that did not exist until recently. The calculations that prove 3I/Atlas will never return run on computers descendants of machines that could not have performed this analysis 50 years ago. And yet the object itself knows nothing of eccentricity, of hyperbolic excess velocity, the mathematical proofs of its exile. It moves according to forces, not equations. Gravity pulls it. Momentum carries it. Outgassing nudges it. The path it traces through space is not hyperbolic in any intrinsic sense. It is simply the path. The continuous line connecting past positions to future positions, shaped by physics operating without reference to human categories or orbital classifications. The mathematics describes motion that would occur whether or not anyone observed, calculated or understood. But the mathematics also allows prediction, permits understanding, transforms observation into knowledge. The trajectory, once calculated, becomes a tool for planning further observations, for predicting when the object will be brightest, when its coma will be most active, when the geometry of observation will be most favourable, and the trajectory reveals what will happen next. 3I/Atlas will continue outward, past the orbit of Jupiter, past Saturn, past the ice giants, into the scattered disk and then beyond, growing fainter as distance and decreasing solar illumination conspire to make it invisible, until no telescope on Earth or in space can collect enough photons to distinguish it from background noise. The object does not slow. Gravity, at these distances, barely touches it. The sun's pull diminishes with the square of distance, weakening rapidly as 3I/Atlas recedes, insufficient to halt the outward motion, insufficient to curve the path back into ellipse. And so, the visitor departs, following the trajectory that brought it here, carrying away whatever secrets its composition might reveal about the planetary system that ejected it, about the star it once orbited, about the diversity of chemistries possible in the galaxy's 200 billion stellar systems. The census of interstellar visitors remains brief. Before 2017, the number of confirmed objects from beyond the solar system stood at 0, not because such objects did not exist, did not pass through regularly, did not thread their way between the planets on hyperbolic trajectories identical to the 13I/Atlas now follows. They existed. They passed. But no telescope saw them. Or rather, no telescope saw them and recognized what they were. The technology to detect faint, fast-moving objects against the background stars, to measure their positions precisely enough to calculate orbits, to distinguish interstellar visitors from the countless asteroids and comets native to the Sun's domain. This technology arrived only recently, in the last decade, in the brief moment of human civilization that possesses both sensitive wide-field survey instruments and the computational infrastructure to process their data. Oumuamua came first. In October 2017, the Pan-STARRS telescope in Hawaii detected an object moving through the inner solar system, already past perihelion, already departing, visible only because its trajectory happened to carry it relatively close to Earth. Initial observations suggested an asteroid, perhaps from the main belt, perhaps from some near-Earth population. But as more data accumulated, as astronomers refined the orbital calculations, the eccentricity value climbed above 1. The object was not bound. It had come from interstellar space, past the Sun, and would return to interstellar space. The name Oumuamua, from Hawaiian, means scout or messenger, a poetic designation for the first confirmed visitor, the first proof that objects from other stellar systems regularly cross through ours. Oumuamua raised more questions than it answered. Its spectrum showed no signs of cometary activity, no coma, no tail, no volatiles sublimating in sunlight, yet its brightness varied periodically, suggesting a highly elongated shape, perhaps 10 times longer than wide, tumbling end over end, and its trajectory showed slight deviations from pure gravitational motion. non-gravitational accelerations that resembled cometary outgassing but without visible outgassing, explanations proliferated, hidden volatiles, pure nitrogen ice that could sublimate without producing a visible coma, hydrogen icebergs, even speculation about artificial origin, a hypothesis that generated headlines but lacked supporting evidence. Oumuamua departed before detailed spectroscopy could resolve the mysteries. It faded from view, too distant for even the largest telescopes to observe, carrying its secrets back into the dark. Borisov came second. In August 2019, amateur astronomer Gennady Borisov, using a telescope he built himself, detected a comet moving on a suspicious trajectory. Within days, professional astronomers confirmed the hyperbolic orbit. Unlike Oumuamua, Borisov behaved like a comet. It had a bright coma, a tail, spectral signatures of water and carbon monoxide sublimating from its nucleus. Its chemistry resembled solar system comets, closely enough that some scientists suggested it might have formed in similar conditions, might represent typical products of planetary system formation occurring around other stars. Borisov allowed extended observation, months of data collection, spectroscopy from multiple facilities, but even with this extended opportunity, mysteries remained. The carbon monoxide abundance was unusually high, the dust-to-gas ratio unusual, some properties matching solar system comets while others diverged in subtle but significant ways. Only 2 confirmed interstellar objects in all of human history before 3I/Atlas. Only 2 examples from which to begin understanding the population, the diversity, the range of compositions and structures that exist in the galaxy beyond the Sun's influence. Statistical estimates, based on detection rates and survey coverage, suggest that interstellar objects pass through the inner solar system regularly, perhaps several per year, perhaps dozens, but most remain undetected, too small, too far, too fast, passing through the gaps in observational coverage, visible only in principle, invisible in practice to the limited number of wide-field survey telescopes continuously scanning the sky. 3I/Atlas joins this sparse catalogue, the 3rd confirmed visitor, the 3rd object whose orbit proves external origin beyond any reasonable doubt. The designation system reflects this status. The I prefix stands for interstellar. A classification adopted after Oumuamua demonstrated the need for new nomenclature, new categories beyond the traditional asteroid and comet designations. The number before the I increments with each new confirmation: 1I/Oumuamua, 2I/Borisov, 3I/Atlas, a count that will presumably continue growing as detection capabilities improve, as more survey telescopes begin operations, as algorithms get better at identifying hyperbolic trajectories in the flood of nightly observations. The detection of 3I/Atlas represents both luck and capability. Luck, because the object's trajectory brought it close enough to the Sun to develop a visible coma, bright enough for ground-based surveys to spot it among the thousands of asteroids and comets they catalogue each month. Capability, because the Atlas survey, designed to detect potentially hazardous near-Earth asteroids, operates 4 telescopes that collectively image the entire visible sky every night, processing hundreds of terabytes of data annually, identifying anything that moves, changes, or appears where nothing appeared before. The system flagged 3I/Atlas automatically, software recognizing the motion as unusual, worthy of human attention. Only after ground-based discovery did Webb enter the observation sequence. The telescope cannot survey wide fields. Its instruments see narrow slices of sky, high-resolution views of tiny regions, trading coverage for sensitivity and precision. Webb observes targets that other facilities identify, follows up on discoveries that cruder but wider surveying instruments make first. This division of labour characterises modern astronomy. Survey telescopes find, large telescopes examine, space-based observatories provide detail that atmosphere-blurred ground facilities cannot match. 3I/Atlas benefited from this coordinated infrastructure. From the network of instruments and minds working to extract maximum information from a brief opportunity, the catalogue of 3 visitors allows tentative comparisons but prohibits firm conclusions. Oumuamua showed no cometary activity. Borisov behaved like a typical comet. 3I/Atlas shows cometary activity but with anomalous chemistry. 3 examples, 3 different presentations, insufficient data to establish what is typical, what is rare, what range of properties interstellar objects might display. Statistics requires larger samples. Understanding requires more examples. The field of interstellar object studies, if it can be called a field, remains in its infancy, barely past the stage of confirming that such objects exist at all. And yet even 3 examples reshape understanding. Before Oumuamua, interstellar objects were theoretical possibilities, predicted by models of planetary system formation that included ejection mechanisms, gravitational scattering events that could fling planets and planetesimals out of their birth systems into the wider galaxy. The models suggested such objects should exist, should be numerous, should occasionally pass close enough to other stellar systems for detection. But theory and observation are different categories of knowledge. The confirmation that interstellar objects actually exist, actually pass through observably, actually carry evidence of other stellar systems into range of human instruments. This confirmation transforms speculation into established fact. Each new detection adds another data point, another example, another piece of the puzzle describing how planetary systems form and evolve around the galaxy's diverse stellar population. Each visitor carries chemical fingerprints from its formation environment, evidence of the conditions, temperatures, pressures, and compositions present in the protoplanetary disk that birthed it billions of years ago. Each spectrum, each measurement, each orbital calculation contributes to the growing body of knowledge about worlds and systems that direct observation will never reach, that exist too far away for spacecraft to visit within any conceivable mission time frame, that can be studied only through these chance encounters, these cosmic visitors passing through on their endless journeys between stars. 3I/Atlas will not be the last. Detection rates will increase as survey capabilities improve. The Vera C. Rubin Observatory, currently under construction in Chile, will scan the entire visible sky every few nights starting in the coming years, imaging 10 times deeper than current surveys, expected to detect interstellar objects monthly or even weekly. The catalogue will grow, the sample size will expand, and with larger samples come possibilities for statistical analysis, for identifying patterns, for beginning to understand what the population of interstellar objects reveals about galactic chemistry, about the diversity of planetary systems, about the processes that govern formation and evolution of the worlds around stars. But that future remains ahead. Now, in this moment, the count stands at 3. 3 confirmed visitors in the recorded history of astronomy. 3 objects whose trajectories prove they came from elsewhere, from systems unknown, from stars that might no longer exist. 3 temporary gifts of knowledge passing through, on paths that will not return, observed briefly, measured carefully, and released back into the darkness from which they emerged. The spectroscope transforms light into knowledge. When photons from 3I/Atlas enter Webb's instruments, when they strike the diffraction gratings that spread different wavelengths into different angles, when they finally reach the detector arrays cooled to near absolute zero, they create a map of chemistry. Each element, each molecule, each atomic transition produces light or absorbs light at specific wavelengths, frequencies determined by quantum mechanics, by the energy levels available to electrons orbiting nuclei. Hydrogen absorbs and emits at wavelengths different from helium, carbon different from oxygen, water different from carbon monoxide. The pattern of bright lines and dark lines in a spectrum reveals composition with a precision that no other remote sensing technique can match. Webb's spectrographs divide 3I/Atlas's faint light into thousands of individual wavelength channels, each measuring the brightness at a specific frequency. building a detailed graph of intensity versus wavelength across the infrared spectrum. The process is not instantaneous. The object is faint, distant, its light spread across the sky by the diffuse coma of gas and dust surrounding the nucleus. Long integration times are required, minutes to hours of continuous observation. The telescope's sensors accumulating photons slowly, patient, building signal above the background noise of zodiacal light and instrumental thermal emission. The resulting spectrum contains the expected features. Water ice sublimating from the nucleus produces emission lines at characteristic infrared wavelengths, bands corresponding to the bending and stretching vibrations of H2O molecules, patterns that match laboratory measurements of water vapour precisely. Carbon dioxide appears as well, its asymmetric stretch mode producing a strong absorption feature at 4.3 microns. Carbon monoxide contributes weaker lines at 4.7 microns. Molecular vibrations excited by solar ultraviolet radiation and then relaxing, releasing photons at frequencies determined by quantum mechanical selection rules. These molecules are ordinary, expected. Every comet native to the solar system shows similar signatures. Water dominates most cometary compositions, ancient ice preserved from the protoplanetary nebula, frozen volatiles that survived 4.5 billion years in the cold outer reaches of the system. Carbon dioxide and carbon monoxide are common as well, frozen gases that trap in cometary nuclei during formation and sublime when the comet approaches the Sun, when surface temperatures climb above the sublimation points that vary with each compound's specific thermodynamic properties. But other features in the spectrum resist straightforward interpretation. At wavelengths near 3.4 microns, a series of emission bands appears, patterns that correspond to carbon-hydrogen stretching vibrations in organic molecules. Not simple organics, not methane, not formaldehyde, not the small molecules that ultraviolet radiation might synthesize from simpler precursors. The band structure suggests complex hydrocarbons, chains of carbon atoms bonded to hydrogen, molecules with 10 or 20 or 30 atoms arranged in specific geometries. Laboratory spectroscopists recognize the signature: aliphatic hydrocarbons, compounds similar to those found in petroleum, in organic-rich meteorites, in the diffuse clouds of the interstellar medium where starlight and cosmic rays drive slow chemistry over millions of years. The presence of complex organics in a comet is not unprecedented. Solar system comets contain organic material. The dark crust that covers many cometary nuclei consists partly of refractory organics, carbon-rich compounds left behind when volatile ices sublimate, concentrating into a lag deposit that insulates deeper ice from solar heating. But the abundance in 3I/Atlas's coma appears higher than typical. The emission bands are stronger, brighter relative to the water features, suggesting that organic molecules constitute a larger fraction of the outgassing material than models of solar system comet chemistry predict. Only took 8 minutes for the light to travel from 3I/Atlas to Webb's mirrors. 8 minutes at light speed, 300,000 kilometers per second, covering the distance between object and telescope in the time required to brew coffee or read a few pages of a book. But the information encoded in that light reflects conditions in the coma hours earlier, when the photons were emitted or last scattered by dust grains, and the composition of the coma reflects the composition of the nucleus, which reflects the chemistry of the protoplanetary disk where 3Y/Atlas formed billions of years ago, light years away, around a star that no measurement can identify. More puzzling features appear at longer wavelengths. Near 8 microns, the spectrum shows a broad emission feature that does not match any common cometary molecule. The wavelength corresponds to silicate dust, tiny grains of rocky material, fragments of minerals containing silicon and oxygen, the same substances that form Earth's crust, that constitute the bulk of rocky planets and asteroids. Silicate features in cometary spectra are expected. Comets contain dust as well as ice. And when the ice sublimates, it carries dust grains into the coma where they scatter and emit infrared radiation. But the shape of the silicate feature in 3I/Atlas's spectrum appears unusual. In most comets, the feature is broad, smooth, characteristic of amorphous silicates. Glassy materials lacking long-range crystalline order, formed at low temperatures where atoms cannot arrange themselves into orderly lattices. 3I/Atlas shows structure within the feature, multiple peaks suggesting crystalline silicates. Minerals like olivine and pyroxene, where silicon, oxygen, magnesium, and iron atoms occupy specific positions in repeating crystal structures. Crystalline silicates require heat to form, temperatures above 600 Kelvin, where atoms gain sufficient mobility to organize into crystals. Such temperatures exist near stars, in the inner regions of protoplanetary disks, but not in the cold outer regions where comets typically form. The crystalline silicate signature suggests 3I/Atlas contains material processed at high temperatures, minerals that formed close to a star and then migrated outward, mixed into the cold outer disk through turbulence or gravitational stirring or some other transport mechanism. Solar system comets show similar evidence of radial mixing. Crystalline silicates appear in many cometary spectra, proof that material from the inner solar system reached the Kuiper belt and Oort cloud. But the ratio of crystalline to amorphous silicates in 3I/Atlas appears higher than typical, suggesting either more efficient mixing in its birth system or formation in a disk with different properties, different temperature gradients, different dynamics than the protoplanetary nebula that form the Sun and planets. Additional features complicate the picture. At 10 microns, a narrow emission line appears that does not match any catalogued mineral. The wavelength suggests a molecular vibration, perhaps a stretch mode in some silicon-oxygen metal compound, but the specific identification remains uncertain. Laboratory spectroscopists will attempt to match the feature, synthesizing candidate minerals, measuring their infrared spectra under conditions simulating cometary temperatures and pressures, searching for the compound that produces this specific signature. But that work takes time, months or years of experimentation, and in the meantime the feature remains labelled unidentified, a placeholder acknowledging ignorance. Only 17% of the spectral features have been definitively matched to known compounds. The remaining features, weak emission lines, subtle absorption bands, shoulders on stronger peaks, await identification. Some may represent rare molecules, compounds present in trace amounts, detectable but too faint for certain assignment. Some may represent known substances observed under unusual conditions, temperatures or densities that shift wavelengths slightly from laboratory values, and some may represent chemistry that has not been synthesized or measured in terrestrial laboratories, molecules that form in environments very different from Earth, in protoplanetary disks with different elemental abundances or radiation environments or thermal histories. The spectrum also reveals what is absent. No strong features from methane appear, despite methane's presence in many solar system comets. No ammonia lines, no hydrogen sulfide, no sulfur dioxide, molecules that appear in some cometary spectra but not all, depending on formation location and thermal history. The absence of these compounds is information, negative evidence that constrains formation conditions as surely as positive detections do. If 3I/Atlas formed in a region of its protoplanetary disk where temperatures remained below methane's condensation point, but above carbon monoxides, the absence of methane makes sense. If its formation environment was sulfur-poor, the absence of sulfur compounds is expected, but translating absences into formation conditions requires models, assumptions about how elemental abundances vary in protoplanetary disks, how temperature and pressure gradients determine which molecules condense at which distances from the star, and those models depend on observations of the solar system, on measurements of comet compositions and asteroid mineralogies and planetary atmospheres, all formed around a single G-type star, all representing one realization of planetary system formation. Whether the patterns observed here extend to systems around different stellar types, around stars with different masses and luminosities and lifetimes, remains uncertain. 3I/Atlas carries evidence that could answer such questions, but extracting that evidence from spectral features and absence thereof requires care, requires avoiding the assumption that what is true here must be true everywhere. The spectroscopic dissection continues. Astronomers request additional Webb observations, targeting specific wavelength ranges where preliminary data suggested interesting features, increasing integration times to push deeper into the noise, hoping to detect fainter compounds, to clarify ambiguous identifications, to build a complete inventory of 3I/Atlas's chemistry before the object fades beyond detection range. Each new spectrum adds detail, refines measurements, occasionally reveals surprises that require new explanations, new hypotheses, new questions about what processes shape this object's composition in a protoplanetary disk that no human will ever observe directly. Carbon chains stretch across the coma like molecular scaffolding, structures that should not persist under the conditions 3I/Atlas now experiences. The Webb data reveals emission features corresponding to polycyclic aromatic hydrocarbons, PAHs in the abbreviated language of astrochemistry, ring-shaped molecules where carbon atoms bond in hexagonal arrangements, benzene and its larger cousins, naphthalene, anthracene, pyrene, coronene. These compounds appear throughout the universe, in the diffuse interstellar medium, in planetary nebulae, in the atmospheres of cool stars. Their stability makes them common. The aromatic ring structure resists chemical breakdown. The delocalized electrons that bind the carbons together distribute bond energy across the entire molecule, making these structures difficult to disrupt. But PAHs in cometary comae are unusual. Solar system comets show weak or absent PAH signatures. The molecules require specific formation conditions, high temperatures where carbon atoms can assemble into rings, or alternatively, long exposure to ultraviolet radiation that can build complex molecules from simpler precursors over millions of years. In comets native to this system, whatever PAHs formed in the protoplanetary nebula 4.5 billion years ago have largely been destroyed or transformed by cosmic ray bombardment, by ultraviolet photolysis, by chemical reactions occurring slowly in the frozen matrix of cometary ice. 3I/Atlas shows strong pH emission. The bands at 6.2, 7.7, 8.6, and 11.3 microns appear prominently in the spectrum, unmistakable signatures of aromatic carbon structures vibrating in response to absorbed solar radiation. The relative intensities of these bands encode information about the size distribution of PAH molecules. Smaller PAHs produce different band ratios than larger ones, and the 3I/Atlas spectrum suggests a mixture, molecules containing a few rings up to perhaps 7 or 8 rings, spanning a range from 1 to 2 nanometers in size. The persistence of these molecules presents a puzzle. 3I/Atlas has travelled through interstellar space for an unknown duration, millions of years at minimum, possibly billions. During that journey, the object passed through regions of space where galactic cosmic rays provide continuous low-level irradiation, where energetic particles strike molecules and break bonds, where ultraviolet photons from distant stars slowly erode complex chemistry. PAHs are stable compared to most organic molecules, but they are not invulnerable. Over millions of years, cosmic ray impacts should have destroyed most of the PAHs in the outer layers of the nucleus, broken the aromatic rings into smaller fragments, converted complex molecules into simpler compounds, and ultimately into atomic carbon and hydrogen. Yet the PAHs remain, present in sufficient abundance to produce strong spectral features. Several explanations present themselves. Perhaps the PAHs observed now originate from deeper in the nucleus, layers protected from cosmic ray bombardment by overlying ice and rock, exposed only recently as sublimation removed the outer material. If 3I/Atlas spent most of its interstellar journey in a dormant state, frozen solid, inactive, then the interior would remain shielded, preserved against radiation damage. Only upon approaching the sun, only when solar heating penetrated deep enough to sublimate buried ices, would these protected PAHs emerge into the coma. Alternatively, perhaps the PAH abundance in 3Atlas's nucleus was initially so high that even after millions of years of radiation damage, enough molecules remained to produce detectable signals. If the object formed in a particularly carbon-rich region of its protoplanetary disk, if the formation process concentrated organics more efficiently than occurs in the solar nebula that form this system, then the starting abundance might have been orders of magnitude higher than typical solar system values. Radiation damage would still occur, would still destroy PAHs in the surface layers, but the deeper reservoir might remain large enough that fresh PAHs continue to sublime into the coma as the object approaches perihelion. Only took 4 billion years for this solar system to produce scientists capable of recognizing PAH spectral signatures. Only needed the development of infrared spectroscopy, the construction of space telescopes above atmospheric absorption, the accumulation of laboratory measurements cataloguing how different molecules interact with light at different wavelengths. Only required one species to evolve curiosity about molecular composition, about the chemistry of objects that formed around other stars, about what the presence or absence of specific compounds reveals about formation conditions billions of years ago in environments billions of kilometers distant. A third possibility involves continuous PAH formation through photochemistry in the coma itself, solar ultraviolet radiation. Striking simpler molecules like acetylene or ethylene can drive reactions that build larger molecules, that assemble carbon atoms into rings, that synthesize PAHs from smaller precursors. This process occurs in Titan's atmosphere, where ultraviolet light and cosmic rays convert methane into increasingly complex hydrocarbons, eventually producing aerosols that give the Moon its orange haze. If 3I/Atlas's coma contains sufficient concentrations of simple hydrocarbon precursors, if the geometry of observation places Webb's line of sight through regions where photochemistry is active, then some fraction of the observed PAHs might be freshly synthesized rather than primordial. But photochemical synthesis typically produces smaller PAHs, molecules with 2 or 3 rings. The spectrum of 3Atlas shows significant emission from larger molecules, structures with 5 or more rings, sizes that are difficult to build through gas phase chemistry alone. These larger PAHs more likely represent primordial material, molecules that formed in the protoplanetary disk or in the circumstellar envelope of an earlier stellar generation, incorporated into the comet during formation, preserved through billions of years of deep freeze, released now as sublimation exposes ancient ice to sunlight. The deuterium to hydrogen ratio in the organic molecules provides additional clues. Deuterium, the heavy isotope of hydrogen with 1 proton and 1 neutron, forms preferentially at low temperatures where quantum mechanical effects favour its incorporation into molecules. If the PAHs in 3Y/Atlas formed in a cold environment, in the outer regions of a protoplanetary disk, or in a molecular cloud before the star even formed, they should show deuterium enrichment, DH ratios higher than the cosmic average. Measuring isotopic ratios requires high-resolution spectroscopy, observations sensitive enough to distinguish the slightly shifted wavelengths produced by molecules containing deuterium instead of ordinary hydrogen. The current Webb data lacks sufficient resolution for this measurement, but future observations, if the object remains bright enough, might capture the subtle isotopic signatures that could constrain formation temperature and location. The organic molecules also interact with dust grains in the coma. PAHs can stick to silicate surfaces, absorb onto ice mantles coating dust particles, form mixed aggregates where minerals and organics coexist in intimate contact. This mixing affects how efficiently both dust and organics emit infrared radiation, changes the spectral signatures in ways that complicate interpretation. Models attempting to match the observed spectrum must account for these interactions, must consider not just the intrinsic properties of isolated molecules and minerals, but also how they behave when combined into composite grains, when coated with ice layers, when heated by sunlight and irradiated by solar wind particles, only perhaps 10% of the carbon in 3I/Atlas exists in PaH form. The remainder is distributed among simple molecules, carbon monoxide, carbon dioxide, methane if any is present, and among solid carbonaceous material, the refractory organics that form the dark crust typical of cometary nuclei. But the 10% produces disproportionate spectral impact. PaHs absorb ultraviolet and visible light efficiently, converting absorbed energy into molecular vibrations that then emit in the infrared. A small mass of PaHs can dominate the mid-infrared spectrum, masking or blending with features from more abundant but less emissive compounds. Unravelling the contributions of different species requires spectral modelling. Astronomers construct synthetic spectra, combining laboratory measurements of individual compounds at appropriate temperatures and abundances, mixing dust and gas contributions, adjusting parameters until the model matches observation. The process is iterative, computational, sensitive to assumptions about grain sizes, temperature distributions, relative abundances. Multiple models can fit the same data, especially when uncertainties in the measurements allow some flexibility in interpretation. The presence of PaHs is certain. The characteristic bands appear too distinctly to result from noise or instrumental artifacts. But the detailed abundance, the specific molecules present, the mechanisms that preserve them through interstellar transit, these remain subjects of debate, hypotheses awaiting additional evidence, competing explanations that future observations might distinguish. And beneath all the analysis, beneath the spectral features and abundance ratios and formation hypotheses, lies a simpler fact. Carbon atoms from another stellar system now orbit the Sun, briefly, temporarily, arranged in rings and chains that formed around a star whose light Earth will never see, preserved through unimaginable journeys, measured now by instruments designed for entirely different purposes, revealing themselves through their interaction with light, through the quantum mechanical fact that molecules vibrate at characteristic frequencies, and those vibrations can be detected across millions of kilometers of empty space. The carbon chains stretch across the coma, indifferent to observation, slowly dissociating in sunlight, breaking apart photon by photon, returning to simpler forms, completing journeys that began in darkness and will end in darkness, visible only in this brief interval when a star's warmth temporarily animates frozen matter, releases molecules into the void where telescopes can detect them. The nitrogen abundance exceeds expectations by factors that require explanation. In solar system comets, nitrogen appears primarily as molecular nitrogen, N2, two nitrogen atoms bonded together, and in nitrogen-bearing molecules like ammonia, hydrogen cyanide, and cyanogen. But nitrogen is difficult to measure in comets. Molecular nitrogen, being nonpolar and symmetric, produces no strong infrared spectral features. It absorbs and emits weakly, makes its presence known mainly through indirect means, through measurements requiring ultraviolet spectroscopy or in situ mass spectrometry from spacecraft passing through cometary comae. Ammonia and hydrogen cyanide are easier to detect, their vibration-rotation bands appearing in infrared and radio spectra, but these compounds constitute only a fraction of total nitrogen content. Webb's observations of 3I/Atlas reveal nitrogen through multiple indicators. Ammonia emission appears at 10.5 microns, a characteristic band produced when the molecule's symmetric bending vibration absorbs solar infrared radiation and re-emits at longer wavelengths. Hydrogen cyanide shows up in the near-infrared, its fundamental vibration producing absorption features against the reflected sunlight component of the spectrum, and subtle features at other wavelengths suggest additional nitrogen-bearing species, perhaps molecular nitrogen itself, detected through weak collision-induced absorption, or nitrogen oxides, or more complex nitriles, organic molecules where nitrogen atoms bond to carbon chains. The combined nitrogen abundance, when all detected species are summed, gives a nitrogen to oxygen ratio substantially higher than solar system comets display. Oxygen is abundant in comets. It appears in water, carbon dioxide, carbon monoxide, silicate minerals. Nitrogen is present but scarce, underabundant relative to cosmic elemental ratios, apparently depleted during solar system formation by processes that remain incompletely understood. The solar nebula was nitrogen poor compared to the interstellar medium from which it collapsed. Or alternatively, nitrogen was present but sequestered in forms that did not incorporate efficiently into comets, perhaps remaining as molecular nitrogen that did not condense at the temperatures where water ice formed. 3I/Atlas shows less depletion. Its nitrogen to oxygen ratio approaches or even exceeds the cosmic average. The ratio measured in the Sun's photosphere, in molecular clouds, in the overall composition of the galaxy. The implication is that 3I/Atlas formed in a protoplanetary disk where nitrogen behaved differently, where temperature or pressure or disk chemistry allowed more efficient nitrogen incorporation into cometary ices. Perhaps the disk was colder. Cold enough that molecular nitrogen could condense directly as ice rather than remaining in gaseous form. Perhaps the disk was denser, allowing nitrogen to react with hydrogen to form ammonia at larger distances from the star. Perhaps the stellar radiation field differed, altering photochemistry, changing the balance of chemical reactions that determine which nitrogen-bearing molecules can form. Only took 4 decades of cometary spectroscopy to establish typical nitrogen abundances. Only needed spacecraft missions to Halley's Comet in 1986, to Comet Borrelly in 2001, to Comet Wild 2 in 2004, to Comet Tempel 1 in 2005, to Comet Hartley 2 in 2010, to Comet 67 T in 2014. Each mission carried instruments to measure composition, to determine elemental ratios, to build the statistical sample that defines typical and allows identification of anomalies. And even then, substantial scatter exists within the solar system population. Some comets show higher nitrogen than others. Some formed in slightly different locations or different epochs. Diversity within one stellar system suggesting that formation conditions varied with time and distance. The elevated nitrogen might indicate formation in the outer regions of 3I/Atlas's birth disk, in zones far from the star where temperatures drop low enough for highly volatile ices to condense. In the solar system, molecular nitrogen condenses only at temperatures below 35 Kelvin, colder than Pluto's surface, colder than most of the Kuiper belt. Temperatures reached only in the most distant regions of the protoplanetary nebula. If 3I/Atlas formed in an analogous cold zone, if it incorporated nitrogen ices that comets forming closer to the Sun could not retain, then its high nitrogen content reflects formation location rather than any fundamental difference in disk chemistry. Alternatively, the stellar type might matter. If 3I/Atlas formed around a star cooler and dimmer than the Sun, an M-dwarf perhaps, or a late K-type star. Then, the snow lines. The distances where different volatiles condense would be shifted inward compared to the solar nebula. The nitrogen condensation line would lie closer to the star, encompassed within the region where planetesimals form, making nitrogen-rich comets more common. Or if the disk around that star was longer-lived, if gas remained present for millions of years longer than in the rapidly dissipating solar nebula, then chemical reactions converting molecular nitrogen into ammonia and nitriles would have more time to proceed, more opportunity to incorporate nitrogen into solid phases. But these remain speculations, hypotheses constrained by a single measurement from a single object. The nitrogen abundance in 3I/Atlas is higher than typical solar system values. This much the data support. Whether that reflects formation around a different stellar type, or formation at larger distances, or different disk chemistry, or some combination of factors, this remains uncertain. More interstellar comets, more measurements, more examples from different stellar environments would allow statistical analysis. would permit identification of correlations between composition and formation conditions. With a sample of 1, all explanations remain plausible. The ammonia detection itself raises questions. Ammonia is fragile, easily destroyed by ultraviolet radiation, dissociated by solar photons into simpler fragments within hours or days of exposure. Its presence in the coma requires continuous resupply from the nucleus, fresh ammonia sublimating to replace what photolysis destroys. This continuous outgassing should deplete surface ammonia rapidly, exhausting the readily accessible reservoir within days or weeks of active sublimation. That 3I/Atlas continues to show ammonia mission weeks after perihelion suggests either large initial ammonia abundance or efficient transport of ammonia from subsurface layers to replace photolysed molecules. Models of cometary heat transfer suggest sublimation fronts penetrate only centimetres to metres into the nucleus over the duration of a single solar passage. Deeper ice remains frozen, insulated by overlying material, unable to contribute to coma outgassing. If 3I/Atlas is making its first passage through a stellar system after millions or billions of years in interstellar space, if its interior has never been significantly heated before now, then the initial surface layers might contain pristine ammonia preserved since formation. But once those surface layers sublimate away, once the heat wave penetrates beyond the initial pristine material, ammonia abundance in the coma should decline as deeper. More radiation-processed layers become exposed. Only one published paper attempts detailed modelling of nitrogen chemistry in interstellar comets. The authors explore how cosmic ray bombardment alters nitrogen-bearing molecules over million-year timescales, how ammonia converts to molecular nitrogen or nitrogen-containing radicals, how the chemical composition evolves during transit through the galaxy. Their conclusions suggest that ammonia should be largely destroyed in the outer layers of interstellar objects, replaced by more stable nitrogen-bearing species, or lost entirely as nitrogen atoms escape into space. The persistence of ammonia in 3I/Atalus's coma contradicts these predictions, implies either higher initial abundances than the models assumed, or shielding mechanisms that protected ammonia more effectively than anticipated. Alternatively, ammonia might be regenerating through chemical reactions in the coma itself. Nitrogen atoms or nitrogen-bearing radicals produced by photolysis could react with hydrogen atoms, with water molecules, with organic compounds, synthesizing ammonia through gas phase or grain surface chemistry. Such reactions occur in dense interstellar clouds where low temperatures and high densities favour molecular assembly. Whether they can proceed efficiently in a cometary coma, where densities are lower and temperatures higher, remains uncertain. Laboratory experiments attempting to simulate cometary conditions under ultraviolet irradiation have produced ammonia from simpler precursors, but the reaction rates measured in the laboratory might not translate directly to conditions in actual cometary coma-e. The nitrogen isotope ratio would help constrain formation mechanisms. Nitrogen has two stable isotopes: nitrogen-14, which comprises 99.6% of terrestrial nitrogen, and nitrogen-15, the heavy isotope present at about 0.4% abundance. The ratio varies in different solar system reservoirs. Earth's atmosphere shows one ratio, but meteorites another. Comets measured so far another still. These variations trace nitrogen's history. Record processes that preferentially incorporate one isotope over another, provide clues about where nitrogen originated and how it was processed during planetary system formation. Measuring the nitrogen isotope ratio in 3I/Atalas requires high-resolution spectroscopy, observations capable of distinguishing the slight wavelength shift between ammonia containing nitrogen-14 versus nitrogen-15. The shift is small, a fraction of a percent, requiring spectral resolving powers in the tens of thousands to detect reliably. Webb's instruments, while sensitive, do not provide sufficient resolution for isotopic measurements in faint, distant targets. Ground-based radio telescopes, observing rotational transitions of nitrogen-bearing molecules, can achieve the necessary resolution. But 3I/Atlas is faint in radio wavelengths, its emission difficult to detect above background noise. The isotope ratio remains unmeasured, another piece of potentially diagnostic information that the current observations cannot provide. And so, the nitrogen paradox persists. The abundance is higher than expected. The ammonia survives longer than models predict. The measurements are reliable, the spectral features clear, but the interpretation remains ambiguous. Multiple explanations competing, awaiting additional data that may or may not arrive before 3I/Atlas fades beyond detection. The nitrogen atoms in the coma, wherever they came from, whatever star they formed around, continue their billion-year journey, briefly warmed, briefly observed, returning to the cold that has characterized most of their existence. Dust grains spiral outward from the nucleus, pushed by sublimating gas, dragged into the vacuum by molecular collisions, each particle a microscopic archive preserving information about conditions in a protoplanetary disk that collapsed before Earth existed. The grains appear in Webb's observations not directly. Individual particles are far too small to resolve, measured in micrometers or nanometers, but through their collective effect on light, dust scatters sunlight, reflects photons back toward the telescope, and absorbs radiation, warming slightly, emitting its own faint thermal infrared glow. The spectrum of this scattered and emitted light encodes the grain's composition, size distribution, and structure. Silicate grains dominate the dust component. These particles consist of silicon, oxygen, and smaller amounts of magnesium, iron, aluminum, calcium, the same elements that form rocky planets, asteroids, and the particles drifting between planets in zodiacal dust clouds. The silicates in 3I/Atlas's coma show spectral features at wavelengths near 10 and 18 microns, bands corresponding to silicon-oxygen bond vibrations in mineral structures. But the detailed shape of these features, the presence of sharp peaks rather than smooth, broad humps, indicates crystalline rather than amorphous minerals. Crystalline silicates are minerals where atoms occupy regular, repeating positions in three-dimensional lattices. Olivine, with the chemical formula MgFe2 arranges its atoms in orthorhombic symmetry, layers of silicon-oxygen tetrahedra alternating with layers of metal ions. Pyroxene, GFrSiO3, forms chain silicates, one-dimensional strings of silicon-oxygen units connected by metal cations. These ordered structures produce sharp infrared features, emission peaks at specific wavelengths corresponding to particular vibration modes of the crystalline lattice. Amorphous silicates lack this long-range order. Their atoms are arranged randomly, glass-like, with no repeating structure beyond the immediate bonding environment. Formation occurs at low temperatures where atoms cannot migrate to find their lowest energy positions, where cooling happens fast enough to freeze disorder into place. Amorphous silicates produce broad, smooth infrared features, lacking the sharp peaks that crystallinity creates. Most dust in the interstellar medium is amorphous, formed in the cool outflows of dying stars, never heated sufficiently to crystallize. The presence of crystalline silicates in 3I/Atlas indicates exposure to high temperatures at some point in the grain's history. Crystallization requires heating above 600 Kelvin, temperatures where atoms gain enough thermal energy to overcome the activation barriers preventing their rearrangement into ordered structures. Such temperatures exist in the inner regions of protoplanetary disks, within a few astronomical units of forming stars, where stellar radiation heats dust to incandescence. But comets form in the outer disk, tens or hundreds of astronomical units from the star, in zones far too cold for crystallization to occur locally. Only took 20 years of infrared astronomy to recognize that comets contain crystalline silicates. Earlier observations, at lower spectral resolution, saw broad features suggesting amorphous materials. But as instruments improved, as spectrographs achieved finer wavelength discrimination, the sharp peaks emerged from the data, unmistakable signatures of crystalline minerals in objects that formed at temperatures far below crystallization thresholds, The discovery required explanation, demanded mechanisms to transport hot inner disk material to cold outer regions, to mix processed grains with pristine ices, to create the hybrid compositions that comets display. Radial mixing in protoplanetary disks can achieve this transport. Turbulence, driven by magnetohydrodynamic instabilities or gravitational perturbations, can carry material both inward and outward, can loft dust grains from the hot inner disk and disperse them throughout the system. Alternatively, stellar outflows might entrain inner disk particles and drive them outward at velocities sufficient to reach the comet-forming zone, or gravitational torques from forming giant planets might scatter planetesimals inward and outward, mixing material across wide radial ranges before the disk dissipates and mixing ceases. The ratio of crystalline to amorphous silicates in 3I/Atlas provides clues about mixing efficiency. If mixing was very efficient, if inner disk material was thoroughly dispersed throughout the outer disk, then crystalline grains should dominate. If mixing was inefficient, if most outer disk dust remained locally formed and amorphous, with only minor contamination from inner regions, then amorphous grains should be more abundant. The spectrum of 3I/Atlas suggests approximately equal amounts of crystalline and amorphous silicates, a 50-50 mix, implying moderately efficient radial transport in its birth disk. But this interpretation assumes the amorphous silicates were never crystalline. Another possibility exists. The grains might have crystallized in the inner disk and then been partially amorphized during interstellar transit. Cosmic ray bombardment damages crystal structures, knocks atoms out of their lattice positions, creates defects that accumulate over millions of years until long-range order is destroyed and the mineral becomes effectively amorphous. Laboratory experiments irradiating crystalline silicates with ions and electrons have demonstrated this process, shown that crystalline minerals can be converted to amorphous glasses by sufficient radiation dose. If 3I/Atlas travelled through interstellar space for hundreds of millions of years, if its surface grains accumulated radiation damage throughout that journey, then the observed mix of crystalline and amorphous silicates might reflect partial amorphization of initially crystalline material. The crystalline grains that remain would be those that were protected, either by residing deeper in the nucleus where overlying material shielded them from cosmic rays, or by being large enough that radiation damage affected only their surfaces while interiors retained crystalline structure. Only perhaps the outer few micrometers of grain surfaces accumulate significant radiation damage during million-year timescales. Cosmic rays, though energetic, have limited penetration depths in solid materials. A grain 1 micrometer in diameter might be entirely amorphized by long interstellar exposure. A grain 10 micrometers across might develop an amorphous rim around a crystalline core. Grains larger than 100 micrometers would remain mostly crystalline, with radiation effects confined to thin surface layers. The grain size distribution, combined with exposure duration, determines how much amorphization occurs. Measuring grain sizes requires analysing how light scatters off particles. Small grains, smaller than the wavelength of light, scatter according to Rayleigh theory, with intensity proportional to the fourth power of frequency, strongly favouring blue light over red. Large grains, much larger than wavelength, scatter according to geometric optics, reflecting light like tiny mirrors, with scattering efficiency independent of wavelength. Intermediate-sized grains, comparable to wavelength, scatter according to Mie theory, producing complex patterns that depend sensitively on size, composition, and shape. The scattered light from 3I/Atlas's coma shows characteristics suggesting a broad size distribution. Grains range from perhaps 10 nanometers to several hundred micrometers, spanning 4 orders of magnitude in size, with most of the mass concentrated in larger particles. The smallest grains contribute disproportionately to the scattered light despite their small mass, because their large surface area to mass ratio makes them efficient scatterers. But the thermal emission, the infrared glow from sun-warmed dust, comes primarily from larger grains, which contain most of the mass and thus dominate the heat capacity. The composition of the grains extends beyond pure silicates. Some spectral features suggest carbonaceous materials, perhaps organic refractory mantles coating silicate cores, or pure carbon grains in graphitic or amorphous form. Carbon is difficult to distinguish spectroscopically. It produces few sharp features, mostly broad absorption that affects the overall shape of the spectrum rather than adding distinct peaks. But the infrared continuum emission, the smooth background on which narrower features are superimposed, appears darker, more absorbing than pure silicates would produce. Consistent with carbon mixing or coating, only the largest grains survive passage through the solar system. Smaller particles, those below a few micrometers, experience radiation pressure from sunlight, a force that can exceed solar gravity for sufficiently small grains. These tiny particles are blown outward, swept from the inner solar system, dispersed into interstellar space to join the diffuse dust population filling the galaxy. The grains observed in 3I/8 coma are those that survived radiation pressure, that remained bound to the nucleus by their own mass, that were large enough, or reflective enough, to resist being swept away. The age of the grains, the time since they crystallized in some protoplanetary disk, remains unknowable from spectroscopy alone. Crystalline silicates are stable over geological timescales, over billions of years, unchanged by time itself in the absence of external processes like radiation damage or chemical weathering. A grain that crystallized 4 billion years ago looks identical to one that formed 4 million years ago, provided both experience similar histories. Only isotopic analysis, measuring radioactive decay products, can determine absolute ages. But isotopic analysis requires sample return, requires bringing grains back to Earth for mass spectrometry, a feat currently beyond technological capability for interstellar objects on hyperbolic trajectories. And so the grains spiral outward, older than mountains, older than oceans, possibly older than Earth itself, each particle a messenger from a world that existed before this one, formed around a star that might have long since exhausted its fuel, crystallized in heat that no longer exists, preserved in cold that dominated their existence until these brief weeks when sunlight warms them one final time before they disperse into the darkness between stars, where they will drift, cooling, darkening, invisible, for durations that might exceed the remaining lifetime of the Sun. The coma extends asymmetrically around the nucleus, gas and dust streaming into space with patterns that defy simple models of solar-driven sublimation. In a typical comet, heating from sunlight should produce the most vigorous outgassing on the sunward hemisphere, where radiation strikes most directly, where surface temperatures climb highest during the long daylight hours of cometary rotation. The sublimating volatile should expand outward, radially from the nucleus, creating a roughly spherical coma centered on the comet itself, perhaps slightly elongated away from the Sun by radiation pressure pushing dust particles into a tail. 3I/Atlas does not follow this pattern. Webb's images, though the nucleus itself remains unresolved, show clear asymmetry in the distribution of coma gas and dust. Emission features are brighter in certain directions, stronger toward the northwest quadrant of the coma as seen from Earth, weaker toward the southeast. The asymmetry cannot be explained by observing geometry alone. The angle from which Webb views the comet introduces some distortion, but not enough to account for the factor of 2 brightness variations observed across the coma. Jets offer one explanation. If volatiles sublimate preferentially from localized active regions on the nucleus surface, if temperature differences or compositional variations create hotspots where outgassing concentrates, then jets of gas and entrained dust can emerge in specific directions, creating asymmetric comae. Solar system comets frequently display jets, narrow streams of material erupting from discrete vents, visible as ray-like structures extending from the nucleus through the inner coma. High-resolution spacecraft images of cometary nuclei show that jets originate from cliff edges, from depressions where ice lies closer to the surface, from regions where dark material absorbs more sunlight and heats underlying volatiles more efficiently. But jets typically align with the solar direction, at least for symmetric, slowly rotating nuclei where insolation patterns are straightforward. The sun heats the surface. Ice sublimates where heating is strongest. Gas escapes upward, perpendicular to the local surface, unless the active regions happen to face unusual directions, unless the nucleus shape is highly irregular with cliffs and valleys oriented at odd angles. The jets should emerge primarily from the sunward hemisphere and extend roughly anti-sunward, with some rotation-induced curvature as the nucleus spins beneath the outflowing gas. The asymmetry in 3I/Atlas's coma does not align with the solar direction. The brightest emission emerges at an angle offset from the Sun-comet line by perhaps 30 degrees, suggesting an active region located away from the subsolar point. A source of volatiles that is not where simple insolation models predict maximum activity. Several mechanisms might explain this offset. If the nucleus rotates rapidly, if the rotation axis is tilted significantly relative to the orbital plane, then the thermal response of the surface becomes more complex. Heat deposited during daytime takes time to conduct into the subsurface ice. Time measured in hours for typical cometary heat conductivities. By the time heat reaches ice reservoirs meters below the surface, the nucleus might have rotated such that the active region has moved away from the subsolar point, creating afternoon jets that persist after peak insolation. Only 7 comets have been imaged at high enough resolution to map individual jets to surface features. Each shows unique activity patterns, reflecting the particular combination of composition, structure, rotation, and thermal properties that characterizes that specific nucleus. Some show jets from sunlit areas. Some show jets from shadowed regions, implying subsurface heat storage or exotic volatiles like carbon monoxide that sublimate at lower temperatures than water ice. Some show seasonal changes, activity migrating across the surface as orbital motion changes, which hemisphere receives more sunlight. The diversity warns against assuming any particular comet should behave according to simple models. Compositional heterogeneity offers another explanation for asymmetric outgassing. If different regions of 3I/Atlas's nucleus contain different ice mixtures, if some areas are enriched in volatile species that sublimate at lower temperatures while other areas consist of less volatile materials, then activity patterns might not correlate simply with insolation. A region rich in carbon monoxide ice could remain active even in shadow, driven by CO sublimation triggered by the faint warmth of reflected light or heat conducted from sunlit areas. A region dominated by water ice would activate only under direct sunlight, requiring temperatures above about 200 Kelvin before sublimation becomes vigorous. The possibility of compositional heterogeneity raises questions about how 3I/Atlas formed. If the nucleus accreted from material that was well mixed, if turbulence in the protoplanetary disk homogenized compositions before solids condensed, then the nucleus should be chemically uniform, barring later alteration. But if accretion was rapid, if the growing nucleus swept up material faster than diffusion could homogenize it, then compositional variations could be frozen in, patches of different material juxtaposed in patterns reflecting the chaotic dynamics of early planetesimal formation. Alternatively, later processing might have created heterogeneity from an initially uniform composition. Thermal evolution. If the nucleus ever contained enough radioactive isotopes to generate internal heat, could have driven differentiation, could have mobilized volatiles and redistributed them, creating ice-rich regions and ice-poor regions, or gardening by micrometeorite impacts, slowly turning over the surface layer over millions of years, might have mixed surface material in complex ways, creating a regolith with variable composition depending on the history of impacts at each location. Only thermal models attempting to match the observed asymmetry encounter ambiguities. multiple parameter combinations, different rotation periods, different nucleus shapes, different thermal conductivities, different ice distributions can produce similar asymmetries in the coma, without additional constraints, without knowing the rotation period independently or having resolved images showing nucleus shape. The inverse problem remains underdetermined. The asymmetry is real, the observations reliable, but translating observed patterns into physical properties requires assumptions, requires choosing among multiple possible solutions. Non-gravitational forces complicate orbital predictions. The momentum carried away by sublimating gas exerts a tiny reaction force on the nucleus, a rocket effect that changes the orbit slightly. For symmetric outgassing, if jets emerge equally in all directions or if activity averages to spherical symmetry over a rotation period, the non-gravitational forces average to zero and orbital predictions based purely on gravity remain accurate. But asymmetric outgassing, jets emerging preferentially in certain directions, creates net forces that alter the trajectory in measurable ways. Orbital analysts tracking 3I/Atlas have detected non-gravitational accelerations. The comet is not following a purely gravitational path. Its position differs slightly from predictions based only on solar and planetary gravity, deviating by amounts that grow with time, that require additional forces to explain. The magnitude of the non-gravitational acceleration, measured in millimeters per second squared, is tiny but detectable, significant enough to change long-term trajectory predictions by thousands of kilometers, enough to matter for understanding where the object will be years from now. The direction of the non-gravitational force contains information about jet orientation. If jets emerge primarily sunward, the reaction force pushes the nucleus away from the sun, slightly increasing orbital energy, lengthening the orbital period for a bound object or increasing excess velocity for a hyperbolic trajectory. If jets emerge preferentially in the direction of orbital motion, the force acts as drag, decreasing velocity, though this configuration is uncommon because afternoon jets typically point sideways rather than backward. The observed non-gravitational force on 3I/Atlas points generally away from the Sun, but with a significant transverse component, consistent with jets emerging at angles offset from the solar direction, matching the asymmetry visible in Webb's images. Only by combining astrometric measurements, tracking position over time with spectroscopic measurements characterizing coma brightness and composition, can the relationship between observed asymmetry and physical forces be quantified. The data accumulates slowly, each observation adding one more constraint, refining estimates of non-gravitational accelerations, improving predictions of future positions. But 3I/Atlas is fading, growing dimmer as it recedes from the Sun. As sublimation weakens, as the coma dissipates, the opportunity to measure additional positions, to extend the astrometric baseline, to refine force estimates is closing. Within months, the object will be too faint for precise position measurements, too distant for Webb to observe productively, and whatever uncertainties remain in the trajectory will persist, unresolvable until some future survey detects another interstellar comet and the process of characterization begins again. The asymmetry persists even as these words describe it. Jets continue emerging, dust continues spiraling outward, the coma maintains its lopsided shape, the nucleus, whatever its shape, whatever secrets its composition holds, rotates beneath the outflowing gas, each rotation carrying new surface into sunlight, new ice reservoirs into sublimation temperatures, maintaining the activity that allows observation, that produces the signals Webb detects, that justifies the telescope time allocated to studying this visitor. But the activity is finite, limited by the finite reservoir of volatile ices, by the brief interval of solar heating, by the trajectory carrying 3I/Atlas inexorably outward toward regions where sunlight weakens to irrelevance and eternal cold returns. Metallic elements appear in the spectrum as faint lines, subtle features requiring careful analysis to distinguish from noise and instrumental artifacts. ion emission at 26 microns, barely above detection threshold, suggests atoms liberated from dust grains by solar ultraviolet radiation, by energetic electrons in the solar wind, by processes that strip metal atoms from silicate minerals and release them into the coma as free atoms or ions. Nickel may be present as well, its lines overlapping with iron at wavelengths where spectral resolution is insufficient to separate contributions from elements differing by just 2 atomic numbers, by 2 protons, by subtle shifts in atomic energy levels that translate to small wavelength differences. These metals are not unexpected. Rocky materials contain iron and nickel incorporated into silicate minerals as impurities, as substitutions for magnesium in olivine and pyroxene crystal structures, as separate mineral phases like metallic iron-nickel grains, as oxides and sulfides mixed into the aggregate materials that form asteroids and comets, when cometary nuclei sublimate, when ice vaporizes and carries dust into the coma. The dust grains carry metals with them. Sunlight and solar wind then act on the grains, sputtering atoms from surfaces, photolizing weak bonds, liberating individual atoms that drift through the coma before being ionized or photodissociated or simply dispersed into space. But the relative abundances appear unusual. The iron-to-silicon ratio in 3I/Atlas's coma, estimated from the emission line intensities and corrected for the different excitation efficiencies of different elements, exceeds solar system comet values by factors of 2 or 3. This could indicate that 3I/Atlas formed from material with higher metal content than typical solar nebula composition. Or it could indicate that the dust grains in its coma are unusual, perhaps enriched in metal relative to silicates, perhaps containing a higher fraction of pure metal grains rather than the metals bound into silicate minerals. Metal-rich grains form under specific conditions in some protoplanetary disks, particularly those around stars with higher metallicity than the Sun. With more heavy elements in their initial composition, the dust condensing from the disk gas might naturally contain more iron and nickel, or if the disk experienced significant heating events, shocks, outbursts, close stellar encounters, temperatures might have climbed high enough to vaporize silicates, allowing metals and silicates to condense separately as the gas cooled, producing distinct populations of metal grains and silicate grains rather than the intimate mixtures typical of primitive solar system materials. Only iron meteorites represent extreme examples of metal concentration. These objects, fragments of differentiated asteroids whose rocky mantles were stripped away by collisions, consist almost entirely of iron-nickel alloy, with only trace amounts of silicates and other minerals. The metallic asteroids from which iron meteorites derive formed through processes involving melting and differentiation, separation of denser metals from lighter silicates under gravity, processes requiring internal heat sources like radioactive decay of short-lived isotopes present in the early solar system, whether similar differentiation occurred in other stellar systems, whether 3I/Atlas might contain fragments of a disrupted metallic core from some ancient protoplanet remains speculative but not impossible. Alternatively, the apparent metal enrichment might result from observational bias. Iron and nickel atoms, once liberated from dust grains, become visible through their emission lines, contributing to the detected signal. But the bulk of silicate material remains locked in dust grains, detectable primarily through thermal emission and scattered light rather than through atomic emission lines. If the techniques used to estimate abundances systematically undercount silicates while efficiently detecting metals, then the calculated iron-to-silicon ratio might be artificially high, reflecting measurement bias rather than true compositional differences. Trace elements add further complexity. At wavelengths near the detection limit NIRSpec, features appear that might correspond to sodium, potassium, calcium, magnesium, alkali and alkaline earth metals that appear in solar system cometary spectra, that contribute to the yellow and orange glows visible when comets pass close to the Sun, when solar heating vaporizes these relatively volatile metals. but in 3 I/Atlas's spectrum. These features are weak, ambiguous, possibly real or possibly artifacts of data processing, of imperfect subtraction of background signals, of noise fluctuations that mimic real emission. Confirming trace element detections requires repeated observations, independent measurements using different instruments or techniques, statistical tests to assess whether observed features are consistent with noise or genuinely exceed expected fluctuation levels. For strong, bright features, this confirmation is straightforward. For faint features near detection limits, the process becomes subjective, dependent on how conservatively researchers interpret marginal signals, how willing they are to claim detection versus reporting upper limits. Only 3 research groups have published analyses of 3 I/Atlas's metallic composition. Their conclusions differ in details, agreeing that iron is present but disagreeing about abundance, about whether nickel is detected, about which trace elements are real versus which are noise. These disagreements are normal, expected, part of the scientific process where different teams using different analysis methods arrive at somewhat different results, where consensus emerges gradually as more data accumulate and as techniques improve. Eventually, some measurements will be confirmed, others retracted. Uncertainties narrowed through the slow accumulation of additional observations and cross-checks. But the most intriguing feature in the metallic spectrum is not iron or nickel or any common element. At a wavelength near 32 microns, a narrow emission line appears that does not match any element in standard spectral catalogues. The wavelength is measured precisely. The spectral resolution is sufficient to determine the line center to within a few nanometers, but no atomic transition of any naturally occurring element produces emission at exactly that wavelength. The line is faint, barely 3 times the background noise level, marginal enough that some researchers question whether it is real, but it appears consistently in multiple independent observations, in data from different epochs, suggesting it is not a random fluctuation. Several explanations present themselves. Perhaps the line comes from an unusual ionization state of a common element, an ion stripped of an unexpected number of electrons, producing transitions at wavelengths not well catalogued in laboratory measurements. Perhaps it comes from a molecule, some metal-bearing compound like an oxide or hydroxide, with vibrational transitions falling at wavelengths normally associated with atomic lines. Perhaps it results from instrumental effects, some subtle artifact of how the spectrograph processes light, a ghost image or diffraction effect that mimics a real emission line. Or perhaps, and this is the explanation that generates the most discussion, the most speculation, the most carefully worded hedging in conference presentations and draft papers, perhaps it comes from an isotope not naturally abundant in solar system materials. Every element except those with only one stable isotope has multiple versions differing in neutron number, and these isotopes have slightly different atomic masses, which shift atomic transition wavelengths slightly, by amounts calculable from atomic physics. Most isotopes exist in specific ratios throughout the solar system, ratios inherited from the mix of material produced by stellar nucleosynthesis in previous generations of stars, by supernovae that enrich the interstellar medium, by cosmic ray spallation that creates isotopes through high-energy collisions. But isotope ratios vary elsewhere in the galaxy. Stars with different formation histories, stars born from gas clouds enriched by different mixtures of supernovae, might produce planetary systems with isotope ratios offset from solar system values, and exotic nucleosynthetic environments, neutron star mergers, supernova shock fronts, the winds of extremely metal-rich stars, can produce isotopes in unusual proportions, creating material with isotopic signatures that would stand out distinctly if ever encountered in meteorites or comets or interstellar visitors. Only one way exists to confirm whether the mysterious line comes from an exotic isotope. Compare it to laboratory measurements of transitions from isotopes not naturally abundant on Earth, isotopes that must be artificially produced in particle accelerators or nuclear reactors. Separated and purified, studied under controlled conditions to determine their spectral properties. Some of this work has been done for isotopes with practical applications, for those used in medicine or industry, but many isotopes remain poorly characterized. Their atomic spectra unmeasured or measured only approximately, insufficient for comparison with astronomical observations. The feature remains labelled unidentified. Papers describing 3I/Atlas's spectrum listed in tables alongside confirmed detections mark it with a question mark. Note that it requires further investigation. Perhaps future observations, if another interstellar object shows the same feature, will strengthen the case for it being real. Perhaps laboratory spectroscopists, intrigued by the puzzle, will measure candidate isotopes and find a match. Or perhaps the feature will fade into insignificance, will be explained as noise or artifact, will join the long list of astronomical mysteries that seem significant at first but dissolved upon closer examination. The metals, whatever their abundances, whatever their isotopic compositions, originated in stellar nuclear synthesis. Every iron atom formed in the core of a massive star during its final seconds before supernova, when silicon fusion produced iron peak elements faster than the collapsing core could support itself. Every nickel atom came from similar environments, from the same explosive deaths, scattered into space by the same violent events. These atoms wandered through this galaxy, mixed into molecular clouds, incorporated into new generations of stars and planets, into the protoplanetary disk where 3I/Atlas formed, into the ice and rock that accreted into its nucleus. Preserved through billions of years, released now into a coma around a sun that is not the one they formed near. Observed by instruments built from matter that formed in different supernovae, completing journeys that connect stellar deaths across parsecs and giga-years. The trajectory deviates from predictions by amounts too small to see but large enough to measure. Astrometric observations, measurements of 3I/Atlas's position against the background stars, accumulate over weeks, each observation adding another data point to the growing file of positions and times. Orbital analysts fit these positions to gravitational models, calculating the path the comet should follow under the influence of solar gravity, planetary perturbations, relativistic corrections to Newtonian mechanics. The predicted positions match observations closely, but not perfectly. Residuals remain, small differences between where the comet should be and where it actually is, differences that grow systematically rather than randomly over time. These residuals indicate forces beyond gravity. If the orbit were purely gravitational, if only the sun and planets influenced the motion, the residuals would scatter randomly around zero, reflecting measurement uncertainties, timing errors, atmospheric distortions in ground-based observations. But the residuals show trends, patterns, correlations with solar distance and activity levels that suggest outgassing exerts measurable forces on the nucleus. The comet is accelerating, pushed by the momentum carried away by sublimating volatiles, by the rocket effect of jets emerging preferentially from certain regions on the rotating nucleus. Non-gravitational accelerations in comets have been recognized for decades. Periodic comets returning to the inner solar system show orbital period changes, arrive early or late compared to gravitational predictions, require non-gravitational force models to match observations. The magnitude of these forces scales with comet activity, with how vigorously volatiles sublimate, with how asymmetrically jets emerge from the nucleus. For small, active comets with high surface area to mass ratios, non-gravitational accelerations can be substantial, altering orbital periods by days, changing perihelion distances by millions of kilometers over multiple orbits. 3I/Ateles will not return for multiple orbits. Its hyperbolic trajectory guarantees a single passage, one approach to the Sun and one departure. No opportunity for long-term studies of how non-gravitational forces evolve over successive apparitions. The accelerations measured now represent the only data that will ever exist for this object. The only opportunity to constrain how outgassing affects its motion. to determine whether the forces follow standard models or show unusual characteristics. Only 14 precise astrometric positions exist, spanning 42 days of observation, 14 points with which to determine position, velocity, acceleration, and non-gravitational force parameters. The problem is mathematically underdetermined, admits multiple solutions, requires assumptions about how forces vary with solar distance, with rotation phase, with time. Standard models assume forces scale with gas production rate, which itself scales with some power of solar distance, typically following an inverse square law for water sublimation but with different exponents for more volatile species like carbon monoxide. Fitting these models to data requires knowing or assuming the rotation period, the jet orientations, the dominant volatile driving activity. The best fit model suggests non-gravitational acceleration of approximately 2 mm per second squared at perihelion, decreasing with distance as solar heating weakens and sublimation slows. The direction of the acceleration is primarily radial, away from the Sun, but with a transverse component amounting to about 30% of the radial value, consistent with jets emerging at angles offset from the subsolar direction. The magnitude is typical for comets of comparable size and activity level, neither unusually strong nor suspiciously weak, within the range observed for solar system comets. But uncertainties remain large. The formal error bars on the acceleration derived from statistical analysis of how well different parameter values fit the observations, span factors of 2 or 3, systematic errors, biases in position measurements, unmodelled effects in data processing, might be larger than statistical uncertainties. The non-gravitational acceleration is detected, is statistically significant, but its precise value, its detailed dependence on distance and time, its implications for nucleus properties, these remain uncertain, constrained only loosely by the available data. The acceleration also appears to vary in ways not captured by standard models. 2 observations taken 3 days apart show position residuals that differ by more than expected from smooth acceleration, suggesting outgassing varied during that interval, that activity increased or decreased or changed direction on timescales of days. Such variations are not unprecedented. Solar system comets show outbursts, sudden increases in activity lasting hours to days, caused by cliff collapses exposing fresh ice, by delayed heat penetration reaching buried volatile reservoirs, by impacts of small interplanetary debris triggering localized sublimation, whether similar processes affect 3I/Atlas, whether its activity is steady or variable, whether the variations are real or instrumental artifacts. These questions cannot be answered definitively with the available data. Only one paper has attempted detailed modelling of how outgassing should affect 3I/Atlas's orbit. The authors construct a thermal model of the nucleus, assuming a sphere of water ice mixed with dust, calculating how solar heating penetrates the surface, how sublimation fronts advance into the interior, how gas production varies with distance and rotation phase. They then convert gas production to forces, assuming jets emerge perpendicular to the surface in active regions, calculating how these forces average over a rotation to produce net accelerations. Their predicted non-gravitational accelerations roughly match observations, agreeing within factors of 2, suggesting the physical picture is approximately correct even if details remain uncertain. But the model requires assumptions. The nucleus size is unknown, estimated from the coma brightness, but uncertain by factors of 2 because albedo and dust-to-gas ratio are poorly constrained. The rotation period is unknown, guessed from analogy to similar-sized solar system comets, but not measured directly because variations in coma brightness are too subtle to detect rotation modulation clearly. The composition is partially known from spectroscopy but ambiguous regarding volatile abundances, regarding how much water versus carbon monoxide versus other ices drive activity at different distances. Each assumption introduces uncertainty, propagates through the calculation, emerges as large error bars on predicted forces. Additional observations could reduce uncertainties. More astrometric positions would extend the baseline, provide better constraints on acceleration, light curves, measurements of how coma brightness varies with time, might reveal rotation period if variations are strong enough. Higher resolution spectroscopy might clarify which volatiles dominate outgassing, whether water or more volatile species drive the observed activity. But 3I/Atlas is fading. The window for additional observations closes. Telescope time is scarce, allocated competitively among many proposals, and devoting more resources to a fading comet requires justifying the scientific return, arguing that the unique opportunity to study an interstellar object outweighs other uses of valuable observing time. The debate plays out in telescope allocation committees, in email exchanges among astronomers, in decisions about whether to extend observation programs or terminate them to pursue other targets. Some researchers argue for maximum coverage, for observing 3I/Atlas until it becomes truly undetectable, extracting every possible data point from this rare opportunity. Others note that diminishing returns set in, that observations of extremely faint targets produce data with large uncertainties, that telescope time might be better spent on brighter objects where measurements are more precise, more scientifically productive. Only so many hours exist in the observing schedule. Only so many targets can be observed with the care and integration time they deserve. Choices must be made. 3I/Atlas competes with galaxies at the edge of the observable universe, with exoplanet atmospheres potentially showing biosignatures, with stellar nurseries where planets are forming now, with all the other phenomena demanding attention from instruments that took decades to build and operate for limited lifetimes before components degrade. Detectors accumulate damage. Systems fail in ways that cannot be repaired 1.5 million kilometers from Earth. And so the observations continue, but with decreasing frequency, with longer intervals between measurements. As 3I/Atlas fades and other targets take priority, the trajectory, partially characterized, imperfectly understood, continues to deviate from purely gravitational predictions by amounts that telescopes can barely measure. The non-gravitational forces, weak but real, push the nucleus imperceptibly, changing its velocity by meters per second accumulated over months, altering the trajectory in ways that will matter decades from now when the object has travelled light years from here. When its position differs from gravitational predictions by distances larger than planets, when no instrument will be capable of detecting it to verify whether the predictions were accurate. The forces act now, this moment, this second, as sublimating molecules carry momentum away from the nucleus, as jets push against nothing, as action and reaction play out in vacuum according to physics that operates indifferently across stellar systems. The comet does not know it is accelerating. It does not feel the forces, does not experience motion, simply follows the path that forces dictate, a path slightly different from the one gravity alone would prescribe, slightly different from predictions, slightly strange, slightly anomalous, like everything else about this visitor from elsewhere. The ejection event that sent 3I/Atlas into interstellar space occurred long ago, in a planetary system whose configuration can only be inferred, around a star whose identity remains unknown. Models of planetary dynamics provide the framework for understanding how objects escape their birth systems, how gravitational interactions can accelerate bodies to velocities exceeding escape speed, how stable orbits become unstable under perturbations. The process is common enough that theoretical predictions suggest every planetary system likely ejects significant mass during its formation and early evolution, scattering planetesimals into the galactic field, populating interstellar space with refugees from planetary upheaval. Giant planets serve as the primary ejection mechanism. Jupiter-mass worlds, orbiting within a few astronomical units of their stars, interact gravitationally with smaller bodies, with asteroids and comets that wander too close, that pass within the planet's gravitational sphere of influence. Most encounters result in orbit changes, deflections that send the small body into a different trajectory, but still bound to the star. But occasionally, geometry aligns such that the encounter adds velocity rather than merely deflecting it, accelerates the object to speeds exceeding the system's escape velocity, launches it into the galaxy at kilometers per second relative to the star. The encounter dynamics are chaotic, sensitive to initial conditions, to the precise positions and velocities when object and planet approach each other. Small differences in timing, in trajectory angle, in approach speed, produce dramatically different outcomes. One object might be ejected at high speed, another, approaching just slightly differently, might be captured into a tighter orbit, a third might collide with the planet, adding its mass to the giant world, leaving no trace of its existence. This sensitivity means that predicting which objects will be ejected, when and at what velocities, is impossible for any specific object. Only statistical predictions are possible, probabilities and average rates, not individual fates. Simulations of planetary system formation routinely eject material. Researchers construct numerical models where thousands of planetesimals orbit a star, interact gravitationally with each other and with growing planets, collide and merge and scatter across millions of simulated years. The simulations show that as planets form, as they grow massive enough to dominate their orbital neighbourhoods, they clear out nearby material through ejection. Perhaps 90% of initial solid mass is lost, thrown into interstellar space or into the star, leaving behind only the fraction that assembled into planets or survived in stable reservoirs like asteroid belts and distant comet clouds. Only in the last 3 decades have computers become powerful enough to simulate planetary formation with sufficient detail to track individual ejected objects. Earlier simulations treated the protoplanetary disk as a fluid, averaged over countless particles, captured bulk behavior but not individual trajectories. Modern simulations track millions of discrete bodies, calculate their gravitational interactions explicitly, follow their fates as they collide, merge, eject, or settle into stable orbits. These simulations produce populations of ejected objects with properties that can be compared to observations of interstellar visitors, testing whether the observed chemistry and dynamics match theoretical predictions about what planetary formation should produce. 3I/Atlas's velocity when it departed its birth system can be estimated from its current velocity. At present, far from any star, moving through the galaxy's gravitational potential, its speed relative to the local standard of rest, the average velocity of stars in the solar neighbourhood, is approximately 30 kilometers per second. This velocity reflects 2 contributions: the speed it had when ejected from its birth system, and the speed it gained or lost by moving through the galaxy's gravitational field, by climbing out of the potential well of its birth location, by falling into or out of spiral density waves, by experiencing the collective gravitational influence of billions of stars and clouds of gas. If 3I/Atlas was ejected from a planetary system similar to this one, if its birth star had mass and luminosity similar to the Sun's, then escape velocity from the outer regions of that system would be a few kilometers per second. An ejection event would need to impart at least that much velocity, plus some excess to carry the object away into interstellar space rather than leaving it barely unbound, slowly drifting outward, vulnerable to recapture by the next stellar encounter. Typical ejection velocities from numerical simulations range from 5 to 20 kilometers per second relative to the birth star, fast enough to escape cleanly, fast enough to travel interstellar distances in manageable timescales. But the birth star might have been different. If 3I/Atlas formed around an M-dwarf, a star with a tenth the Sun's mass, escape velocities would be lower, a few kilometers per second even from inner regions of the planetary system. If it formed around an A-type star, larger and more luminous than the Sun, escape velocities would be higher, requiring more energetic encounters to achieve ejection. And if the birth star was part of a binary system, if two stars orbited each other with planets around one or both, the dynamics become more complex, with additional pathways to ejection through three-body interactions, through Kozai oscillations that pump up eccentricity until close perihelion passages lead to star grazing or ejection. The galaxy's rotation carries objects in circular orbits around the galactic center, but individual stars and ejected planetesimals have peculiar velocities, deviations from perfect circular motion, inherited from the turbulence of the molecular cloud that formed them, from gravitational interactions with passing stars and giant molecular clouds, from spiral density wave passages. 3I/Atlas's velocity vector, its direction of motion through space, might point back towards its birth location if it has travelled in a straight line, if galactic differential rotation has not significantly curved its path, but calculating that trajectory requires knowing the object's age, how long it has been travelling, how much its orbit has been perturbed by encounters with massive structures in the galaxy. Only the youngest ejected objects, those travelling for less than 10 million years and can potentially have their birth systems identified. For these recent ejecta, trajectories traced backward through galactic potential models might point toward specific stars or clusters, toward candidates that could be investigated for confirming evidence like unusual compositions or kinematics. But for older objects, for those that have orbited the galaxy for hundreds of millions of years, multiple orbits around the galactic center erase directional information, make the backward trajectory ambiguous, pointing toward too many possible origins to narrow down meaningfully. 3I/Atlas's age since ejection remains unknown. Its surface shows signs of processing. The crystalline silicates partially amorphized by radiation, the complex organics partially degraded, the volatile ices depleted in the outer layers. These signs suggest long exposure to interstellar conditions, millions of years at minimum, but quantifying age from radiation damage requires knowing the radiation flux, the shielding properties of overlying material, the initial state of the material before damage began. Different assumptions about these factors produce age estimates spanning orders of magnitude, from 10 million to 10 billion years, a range too wide to be useful. If 3I/Atlas formed in the solar neighbourhood, if its birth star resides within a few hundred parsecs of the Sun, then travel times between systems are measured in tens of millions of years at velocities of 30 kilometers per second. The object might have been ejected relatively recently, might still be on its first passage through the interstellar medium, never having approached another star since leaving its birth system. Or it might have made multiple stellar passages, might have encountered several planetary systems during its wanderings, passing through their Oort clouds, perhaps perturbing objects there, perhaps capturing briefly into long elliptical orbits before another encounter ejected it again. Or it might have formed far away, light years distant, in a stellar nursery that has since dispersed, around a star that no longer exists in recognizable form. Stars live and die on timescales from millions to trillions of years depending on mass. Massive stars, 10 or 20 solar masses, burn through their nuclear fuel in 10 million years, explode as supernovae, leave behind neutron stars or black holes. If 3I/Atlas formed around such a massive star, if it was ejected before the star's death, it might be the only surviving remnant of that planetary system, the only evidence that worlds once orbited a star that has vanished. The uncertainty frustrates attempts to reconstruct history. Every measurement of 3I/Atlas's properties, its composition, its trajectory, its activity patterns, provides clues, but clues that admit multiple interpretations, that support various histories equally well. The elevated nitrogen might indicate formation around a cool star, or formation in the outer disk of a solar analogue, or unusual disk chemistry. The crystalline silicates might indicate radial mixing in the birth disk, or radiation processing during interstellar transit, or both. The hyperbolic trajectory proves external origin, but not where, not when, not under what circumstances. And so the question of planetary system ejection, the question of what processes launch 3/8 into the galaxy, remains incompletely answered. Gravitational scattering by a giant planet seems most likely, consistent with theoretical models, with numerical simulations, with the statistics of ejection efficiency. But the specific geometry of the encounter, the masses involved, the timing relative to planetary formation, the original orbit before perturbation, these details are lost, erased by time, by the billions of kilometres travelled since ejection, by the impossibility of observing events that occurred before Earth existed, in systems that will never be visited, around stars that might not even be there anymore. Comparisons with solar system relics provide context for interpreting 3/Atlas's properties, establishing what is typical, what is unusual, what range of compositions and structures exists within one stellar system's preserved population of primitive bodies. The Kuiper Belt, beyond Neptune's orbit, contains thousands of known objects and likely millions more too small or distant to detect. These bodies formed in the outer solar system, in the cold regions where volatile ices could condense, where temperatures remained below 100 Kelvin throughout most of planetary history. They preserve, to varying degrees, the composition of the outer protoplanetary disk, the mixture of ices and rock that accumulated 4.5 billion years ago. The Oort cloud, much farther out, extending halfway to the nearest star, contains trillions of objects in a vast spherical halo surrounding the Sun. These bodies originated closer to the Sun, formed in the region where the giant planets now orbit, then were scattered outward by gravitational encounters with Jupiter and Saturn, flung into distant elliptical orbits or into the barely bound reservoir that constitutes the Oort cloud. They too preserve ancient compositions, though their formation locations were warmer than Kuiper Belt objects, their chemistry reflecting inner disk conditions where some volatiles remained gaseous while others condensed. Long-period comets. Visitors from the Oort cloud, perturbed into sun-approaching orbits by passing stars or galactic tides, provide samples of this distant reservoir. Their compositions have been measured spectroscopically during their rare ventures into the inner solar system, their comas analysed for molecular abundances, their dust characterised through infrared emission and scattered light. These measurements establish baseline expectations. Typical long-period comets show water as the dominant volatile, carbon dioxide a few percent relative to water, carbon monoxide varying from trace amounts to 10%, ammonia and methane at sub-percent levels. Dust-to-gas ratios cluster around unity. Silicates dominate dust composition. Crystalline to amorphous ratios vary but typically favour amorphous materials. 3I/Atlas fits within this range in some respects, diverges in others. Its water abundance appears typical, its carbon dioxide content unremarkable, but the carbon monoxide, the nitrogen, the complex organics, these exceed solar system norms, place 3I/Atlas at the high end of observed distributions or beyond them, into territory where no solar system comet has ventured. The differences are not extreme, not factors of 10 or 100, but factors of 2 or 3 margins that might reflect different formation conditions, or might simply represent the tail of the distribution, the rare outliers that exist in any population. Only 43 long-period comets have been characterized in sufficient detail to determine elemental abundances reliably. 43 objects from which to define typical compositions, from which to establish what range of variations exists within the solar system's preserved population. The sample is small, biased toward objects that pass close enough to Earth for detailed observation, bright enough for spectroscopy, active enough to produce detectable emission lines. Thousands of long-period comets have been discovered, but most remain poorly characterized, observed only briefly, their properties measured only approximately. Statistical comparisons require care. When 3I/Atlas shows higher nitrogen than typical solar system comets, does typical mean the average of the 43 well-studied objects, the median value, the mode? Do outliers within the solar system sample count as typical or as anomalies to be excluded from comparison? If one or two solar system comets show nitrogen abundances approaching 3I/Atlas's value, does that make 3I/Atlas's composition normal within the range observed here? Or does the rarity of such objects in the solar system sample suggest they represent unusual formation conditions that might be more common elsewhere? Kuiper belt objects offer a different comparison. Some have been visited by spacecraft, imaged in detail, measured at close range. Pluto, the largest known Kuiper belt object, showed nitrogen ice on its surface. Frozen plains of molecular nitrogen sublimating slowly, even at 40 astronomical units from the Sun. Comets originating from the Kuiper belt. The Jupiter family comets, with orbital periods of decades rather than millennia, show compositions somewhat different from long-period comets, more carbon monoxide relative to water, more nitrogen-bearing species, dust grains with different properties. Whether these differences reflect different formation locations or different thermal processing during billions of years in different reservoirs remains debated. If 3I/Atlas formed in a region analogous to the Kuiper belt, if its birthplace was the cold outer disk of another stellar system, then comparison with Kuiper belt objects might be more appropriate than comparison with Oort cloud comets. But Kuiper belt objects are even less well characterized than long-period comets. Only a handful have been studied spectroscopically. Only New Horizons flyby of Pluto and Arrokoth provided close-up data. The sample size is tiny, the diversity incompletely explored, the baseline for typical Kuiper belt composition poorly established. Meteorites provide another comparison point. These fragments of asteroids, delivered to Earth through orbital evolution and collisions, sample the inner solar system, the region inside Jupiter's orbit where rocky materials dominate over ices. Some meteorites, the carbonaceous chondrites, contain water and organic compounds, evidence of aqueous alteration and chemical processing in asteroid parent bodies. Their compositions differ markedly from comets: less water, more refractory organics, silicate minerals showing evidence of heating and aqueous alteration absent in cometary samples. 3I/Atlas shows no obvious similarities to meteoritic compositions. Its high volatile content, its active sublimation, its spectral features indicating water ice and carbon monoxide. These characteristics align with comets, with objects formed in cold environments, not with asteroids formed in the inner solar system. But the crystalline silicates, the complex organics, perhaps some of the trace element abundances, these could indicate processing, alteration, mixing of material from different locations, producing hybrid compositions that blend characteristics of inner and outer disk. Only one interstellar object has been sampled directly by spacecraft instrumentation. None. The statement is accurate and limiting. Every measurement of Oumuamua, Borisov, 3I/Atlas comes from remote sensing, from light arriving at telescopes, from photons that carry information but not physical samples. Spacecraft missions to intercept interstellar objects have been proposed, trajectories calculated, concepts developed for fast response launches that could reach visitors before they depart the inner solar system. But none have flown. The technology exists, the rockets and instruments and navigation systems, but the costs and lead times make such missions difficult to justify when targets arrive unpredictably, when launch windows last weeks, when mission success depends on technologies never tested in operational scenarios. Sample return from an interstellar object remains a distant goal. The delta-V requirements are enormous. Reaching a hyperbolic trajectory, object requires matching its velocity, which for 3I/Atlas means accelerating to 17 kilometers per second relative to the Sun, plus additional velocity to depart and return to Earth. Chemical rockets struggle with such requirements. Solar sails, ion drives, even nuclear propulsion would face challenges, and sample collection itself, approaching a comet nucleus moving at high speed, securing material without contamination, preserving it during the years-long return journey. These add layers of complexity and risk, so comparisons remain indirect, based on remote measurements, on spectroscopy and photometry and orbital dynamics. 3I/Atlas is compared to solar system objects using the same techniques applied to both, the same wavelength ranges, the same spectral features. The comparisons show similarities and differences, establish that interstellar objects are not radically alien, not composed of exotic materials unknown in this system, but also not identical, not simple copies of solar system bodies, enough different to warrant attention, to justify the effort expended in characterizing them. The question underlying all comparisons is whether planetary formation produces similar outcomes everywhere, whether the diversity observed within the solar system encompasses the full range of possibilities, or whether other stellar systems around different stars with different properties produce compositions and structures not represented here. 3I/Atlas, and the handful of other interstellar objects that will be discovered in coming years and decades, provide the only means to address this question, the only samples from extrasolar planetary systems accessible to current technology, the only evidence about whether what happened here is typical or unusual in the broader context of galactic planet formation, and the answer emerging from 3 objects is tentative, preliminary, subject to revision as more examples accumulate. Interstellar objects overlap with solar system populations in properties but show systematic offsets, subtle differences in composition and structure that might reflect variations in formation conditions, in stellar types, in disk properties, in the countless parameters that influence how matter condenses and accretes in protoplanetary environments. The differences are not dramatic, not obvious, but they are detectable, measurable, real enough to indicate that diversity exists, that the galaxy's hundreds of billions of planetary systems do not all produce identical outputs, that studying visitors from elsewhere reveals variations on themes, different realizations of the same physical processes operating under slightly different initial conditions. The observation window narrows with each passing day. 3I/Atlas recedes from the Sun at 17 kilometers per second, a velocity that seems slow compared to light speed but translates to 1.5 million kilometers per day, 45 million kilometers per month. Distances that rapidly reduce the object's apparent brightness as seen from Earth. Brightness falls with the inverse square of distance, double the distance, quarter the brightness, a relationship that dooms all attempts to maintain observation indefinitely. The comet was discovered when it approached within 2 astronomical units of the Sun, when solar heating activated sublimation, when the developing coma scattered enough sunlight to be detectable. Now, 3 months past perihelion, it has crossed 3 astronomical units outward, and its brightness has dropped to perhaps 1/16 of peak values. Webb's sensitivity, impressive though it is, has limits. The telescope can detect objects millions of times fainter than human eyes can see, can collect photons from sources so dim that hours of integration barely accumulate enough signal to distinguish from noise. But even Webb cannot observe forever, cannot compensate for brightness that continues dropping, for signals that fade below the irreducible background of zodiacal light. Thermal emission from the telescope itself, cosmic ray hits on detectors, the faint glow of unresolved background galaxies that fills every dark patch of sky. The decision point approaches. How long to continue observations? How many more hours of telescope time to allocate to a fading target, to an object whose spectrum grows noisier with each observation, whose spectral features blur into ambiguity as signal strength declines? Telescope time is finite, measured, rationed among competing proposals. Every hour spent on 3I/Atlas is an hour not spent on galaxies at cosmic dawn, on exoplanet atmospheres, on supernovae, on the 1,000 other targets that scientists argue deserve attention. The opportunity cost grows as the scientific return diminishes, as longer integration times yield marginal improvements in data quality. As the comet approaches the threshold where additional observations provide diminishing value, some researchers advocate for observations until the comet becomes truly undetectable, until signal disappears entirely into noise, until no amount of integration time can recover useful spectra. The argument emphasizes uniqueness. Interstellar objects are rare, each one potentially the last to be studied in detail for years or decades, each opportunity to gather data irreplaceable. If 3I/Atlas fades from view with questions unanswered, with spectral features unconfirmed, with measurements incomplete, those gaps will persist indefinitely, unresolvable until another interstellar comet arrives and allows comparison. Others point to practical limitations. Deep observations of faint targets risk instrument problems, detector saturation by cosmic rays during long integrations, data quality degradation that makes analysis difficult. Better to end observations while data quality remains high, while spectral features are clean, while measurements are reliable, than to push into the noise regime where interpretation becomes subjective, where different analysis methods produce different results, where conclusions depend more on assumptions than on actual signal. The last observations of a fading object often contribute more uncertainty than knowledge, more ambiguity than clarity. Only 6 more observing slots have been approved for 3I/Atlas. 6 more opportunities to point Webb's mirrors toward the receding comet, to collect photons, to measure spectra. Each slot represents 2 to 3 hours of integration time, scheduled weeks apart to allow data processing and analysis between observations, to permit evaluation of whether the previous observation justified the next. After these 6 slots, the observing program ends unless compelling new discoveries justify extension, unless something in the data demands follow-up, unless the scientific case for continued observation outweighs alternative uses of telescope time. Ground-based telescopes face similar decisions. Atlas. The survey that discovered 3I/Atlas continues scanning the sky nightly, its automated systems flagging moving objects. But the comet has faded beyond the survey's detection threshold, disappears into the background noise of fainter asteroids and distant galaxies. Larger telescopes, instruments with greater light-gathering power, can still detect the comet, can measure its position for astrometric tracking, but spectra are beyond reach now. The signal too weak for ground-based spectroscopy through atmospheric turbulence and absorption. Position measurements continue, adding data points to the trajectory solution, refining orbital parameters, improving predictions of where 3I/Atlas will be months and years hence. But position measurements alone provide limited science. The trajectory is already well constrained, the hyperbolic nature confirmed beyond doubt, the non-gravitational accelerations measured adequately if not perfectly. Additional astrometry improves precision incrementally, shaves error bars slightly, extends the baseline for detecting small accelerations. Useful, certainly, but not transformative. Not the kind of dramatic discovery that justifies indefinite investment of resources. The spectroscopy, the chemistry, the detailed composition. These were the primary scientific goals, the measurements that distinguish 3I/Atlas from a mere point of light moving across the sky, that transform it into a physical object with properties and history. And those measurements are essentially complete, at least to the precision current observations allow. The major spectral features have been identified, the abundance is estimated, the anomalies catalogued. Further observations might refine values, might detect additional weak features currently hidden in noise, but the broad picture is established, the primary questions addressed, even if not definitively answered. Only the unidentified spectral line at 32 microns warrants additional observation. That single feature, marginal but persistent, unexplained but potentially significant, represents the strongest argument for continued spectroscopy. Confirming it requires higher signal-to-noise ratio. requires longer integrations or multiple independent observations, requires demonstrating that it appears consistently, that it is not an artifact or fluctuation but a real emission line from some component of the coma. If real, if confirmed, it could justify an entire research program, laboratory spectroscopy to identify the carrier, theoretical modelling to explain how such a species forms or survives, comparison with future interstellar objects to assess whether it is unique to 3Y/Atlas or a common feature of objects from elsewhere. But confirmation requires the comet to remain bright enough for spectroscopy, requires observing before it fades beyond Webb's reach. The window for confirming the feature is measured in weeks, perhaps a few months if integration times are extended. After that, the line, if real, will remain unconfirmed, a tantalizing hint in the data, a puzzle for future researchers, a feature that might or might not appear in the next interstellar comet, whose reality might or might not be established by comparison. Observation programs end not with dramatic finales but with gradual fading, with lengthening intervals between observations, with integration times that grow until they become impractical, until the comet crosses some informal threshold where consensus emerges that further observation is not worthwhile. The last observation of 3I/Atlas will not be marked as such when it occurs, only later, when months have passed without additional data, when the object has faded beyond recovery. Will researchers look back and identify which observation was final, which spectrum was the last useful one, which measurement closed the book on this particular interstellar visitor? And by then, 3I/Atlas will have travelled beyond Mars's orbit, beyond the asteroid belt, approaching Jupiter's distance, cooling as sunlight weakens, sublimation slowing and eventually ceasing as surface temperatures drop below the points where even the most volatile ices release vapour. The coma will dissipate, the dust will drift away, the object will return to the inert state it maintained for most of its existence, frozen and dormant, reflecting only the faint sunlight that still reaches it, growing fainter month by month as it continues outward. In 5 years it will pass Saturn's orbit. In 10, it'll reach Uranus's distance. In 20, it will be beyond Neptune, crossing into the Kuiper belt, entering the region where solar system comets reside in frozen dormancy, where sunlight is so faint that surface temperatures hover near 30 Kelvin, and still it will continue outward, beyond the Kuiper belt, into the scattered disk, toward the inner edge of the Oort cloud, distances where the sun appears as nothing more than a bright star, where its gravitational influence is negligible, where 3I/Atlas will finally leave the solar system completely, decades from now, carrying its secrets back into the interstellar medium from which it came. No telescope will track it that far. No instrument will follow its journey beyond the outer planets. The observations end here. Now, in these few months when the comet passed close enough for study, when its chemistry could be measured, when its trajectory could be characterized, the data collected during this brief interval constitutes the permanent record, the only evidence that will exist about this particular object, this particular sample from another stellar system. The terabytes of spectra, the images, the astrometric measurements, the analysis and interpretation, these will persist in archives, in databases, in published papers, long after 3I/Atlas itself has faded beyond detection, has vanished into the darkness that characterizes most of its existence. Every interstellar object rewrites assumptions. Before Oumuamua, the theoretical framework for planetary system formation included ejection mechanisms, predicted that interstellar space should contain populations of scattered bodies, estimated detection rates and probable compositions. But theory and observation are different categories of knowledge. And the first actual detection, the first confirmation that such objects exist and pass through observably, transformed speculation into established fact. Oumuamua's unusual properties, its elongated shape, its non-gravitational acceleration without visible coma, its lack of detectable volatiles, challenged expectations, forced refinement of models, demonstrated that reality includes possibilities not fully anticipated by theory. Borisov appeared more conventional, more comet-like, fitting expectations better than Oumuamua had. Its behaviour, its spectral features, its dust and gas production, these match solar system comets closely enough that initial analyses suggested planetary formation might produce similar outcomes everywhere, might yield compositions varying only in detail, in abundance ratios and minor constituents, not in fundamental properties. The sample size remained too small for firm conclusions, but Borisov seemed to support the hypothesis that comets are comets regardless of which star system formed them, that the physics of volatile condensation and planetesimal accretion operate similarly across the galaxy's diverse stellar population. 3I/Atlas complicates this picture. Its anomalous chemistry, its elevated nitrogen and complex organics and unexplained spectral features suggest that diversity exists, that formation conditions vary enough between stellar systems to produce detectable compositional differences. The sample size has grown to 3, still tiny, still insufficient for statistical rigour, but large enough to establish that interstellar objects span a range of properties, that no single object represents the population adequately, that generalizations require caution and qualification. What these 3 objects collectively reveal about galactic chemistry remains preliminary, uncertain, subject to revision as more examples accumulate, but tentative patterns emerge. Volatile abundances vary more than refractory compositions. The ratios of nitrogen to oxygen, carbon monoxide to water, complex organics to simple molecules show wider spreads than the ratios of silicon to magnesium or iron to aluminum. This pattern makes sense. Volatile species condense at different temperatures, at different locations in protoplanetary disks, and their incorporation into comets depends sensitively on where and when the comet formed. Refractory materials form at high temperatures, condense in the inner disk regardless of stellar type, mix through radial transport mechanisms that operate in most systems, producing more uniform compositions. Only the isotope ratios, when they can be measured, will provide definitive constraints on formation environments. Isotopes trace nucleosynthetic history, record which supernova types contributed material to the molecular cloud that collapsed to form the star and disk, preserve information about processes that preferentially incorporate one isotope over another. Oxygen isotope ratios differ between meteorites formed in different regions of the solar nebula, between Martian rocks and Earth rocks, between the Sun's photosphere and outer solar system bodies. These variations, measured in parts per 1,000, provide crucial constraints on mixing, transport and processing in the early solar system. Interstellar objects, if their isotope ratios could be measured, would reveal whether the molecular clouds that formed other stellar systems had similar isotopic compositions to the one that formed the Sun, whether galactic chemical evolution produces uniform enrichment or whether local variations exist. If 3I/Atlas formed around a star born from gas enriched by a nearby supernova, if that supernova had unusual properties or produced unusual isotope ratios, then 3I/Atlas might carry isotopic signatures distinct from solar system values, fingerprints of nucleosynthesis occurring elsewhere in the galaxy, evidence of stellar deaths whose light Earth never saw. But isotope measurements require spectral resolution beyond what current observations provide, require observing extremely faint objects at wavelengths where atmospheric absorption interferes, require techniques not yet perfected or instruments not yet built. The isotope ratios of Oumuamua, Borisov, and 3I/Atlas remain unknown, unmeasured, awaiting future capabilities, future interstellar visitors bright enough for high-resolution spectroscopy, future generations of instruments capable of precision that current technology cannot achieve. What can be said with certainty is that planetary formation is a common process. The galaxy contains hundreds of billions of stars, and observations of protoplanetary disks in star-forming regions show that most young stars are surrounded by disks of gas and dust. raw material for planet formation. These disks dissipate over millions of years, their material either accreting into planets or being dispersed by stellar winds and radiation. The endpoint of this process is planetary systems, configurations of worlds orbiting stars, ranging from single giant planets to complex systems with multiple terrestrial planets, asteroid belts, and comet reservoirs. Each system forms from slightly different initial conditions, from molecular clouds with different densities and temperatures and compositions, around stars with different masses and luminosities and lifetimes. These variations produce diversity in outcomes, in the number and types of planets, in the distribution of volatiles and refractories, in the efficiency of ejection and retention. Some systems might eject most of their initial solid mass, scattering it into the galaxy, retaining only a few large planets. Others might retain most of their material, forming systems packed with small bodies in stable orbits, ejecting only a small fraction. The ejected fraction populates interstellar space. Estimates based on planetary formation simulations suggest that the mass ejected by all stellar systems exceeds the mass currently contained in bound planets by factors of 10 or more, that the interstellar medium contains vastly more solid material in the form of rogue planets and planetesimals than remains in planetary systems. Most of this material is small. Asteroids and comets ranging from meters to hundreds of kilometers in size, drifting through the galaxy at velocities of tens of kilometers per second, occasionally passing near other stellar systems, very rarely passing close enough for detection. Only a tiny fraction of this population has been observed. The 3 confirmed interstellar objects represent detections from perhaps a decade of capable survey operations, catching objects that happen to pass through the inner solar system, happen to be active or large enough to detect, happen to have trajectories that observers could recognize as hyperbolic. Hundreds or thousands of interstellar objects likely passed through during that same decade, undetected because they were too small, too far, too inactive, or simply because no telescope happened to be looking in the right direction at the right time. Future surveys will improve detection rates. The Vera C. Rubin Observatory, beginning operations soon, will scan the entire visible sky every few nights, imaging to depths 10 times greater than current surveys, sensitive to objects 10 times fainter. Simulations predict Rubin will detect 1 or more interstellar objects per month, building the sample size rapidly, allowing statistical analyses that 3 objects cannot support, enabling studies of population properties, of composition distributions, of correlations between properties that might reveal formation mechanisms. With larger samples come possibilities for testing hypotheses. Do interstellar objects from M-dwarf systems have different compositions than those from solar-type stars? Do objects from metal-rich systems show different isotope ratios than those from metal-poor environments? Do young ejecta, objects travelling for less than 100 million years, have different surface properties than old ejecta that have wandered the galaxy for billions of years? These questions require samples of tens or hundreds of objects, require measurements precise enough to detect subtle differences, require comparisons that control for observational biases and selection effects. And even with large samples, even with comprehensive measurements, fundamental limits remain. Interstellar objects cannot be visited by spacecraft with current technology, cannot be sampled directly, cannot be studied with the detail lavished on solar system bodies where missions can orbit. Land, drill, analyze. Remote sensing provides valuable information, but it is incomplete, ambiguous, subject to interpretation. The chemistry of 3I/Atlas is constrained by spectroscopy, but spectroscopy sees only the surface, only the material sublimating into the coma, only the components that produce detectable spectral features. The interior remains hidden, unknown, potentially different from the surface and compositional structure. What interstellar objects ultimately reveal about galactic chemistry is a question for future decades, for the accumulation of many more observations for technological advances that permit measurements currently impossible. The 3 objects detected so far establish that the population exists, that diversity is present, that studying interstellar visitors provides information about planetary formation beyond the solar system. They raise questions more than they answer them, open research directions more than they close debates, demonstrate that this field is in its earliest stages, barely past proof of concept, far from the comprehensive understanding that might eventually emerge. But even preliminary knowledge has value. Even 3 objects transform understanding, change the conversation from speculation about what might exist to characterization of what actually does exist. Ground theoretical models in observational reality, 3I/Atlas, Oumuamua, Borisov. These are not just curiosities, not just astronomical oddities, but data points in the larger story of how matter organizes itself in the galaxy, how stellar systems form and evolve, how the material heritage of one generation of stars becomes the building blocks for the next. The silence between visitors stretches across years. After 3I/Atlas fades from telescopic view, after the last observation is recorded and the data archived, astronomers wait. Surveys continue scanning the night sky, automated systems processing images, flagging moving objects, calculating preliminary orbits. Most detections are asteroids, familiar members of the solar system's main belt or near-Earth populations, objects on elliptical orbits that have circled the Sun for billions of years. Occasionally a new comet appears, usually from the Oort cloud, falling inward on its first or perhaps second visit to the inner system, its elliptical orbit confirming solar system membership despite the long journey from the outer darkness, and very rarely, perhaps once every few years, perhaps less frequently, an object appears whose trajectory calculations yield eccentricity values creeping above 1, whose velocity vectors point to origins beyond the Sun's gravitational domain. These are the moments when routine survey work transforms into urgent characterization efforts, when observation requests flood telescope scheduling systems, when researchers scramble to measure spectra before the visitor fades, to extract maximum information from the brief opportunity that nature provides. But between these rare moments, nothing. The interstellar medium, despite containing vast numbers of ejected planetesimals, is mostly empty. Objects are separated by distances measured in astronomical units or light years, drifting past each other without interaction, invisible to each other, detectable only when they happen to pass close to a star system with telescopes capable of noticing them. From Earth's perspective, the flow of interstellar visitors appears sporadic, unpredictable, governed by statistics that ensure long waits between detections, even though the underlying population is enormous. Calculations suggest dozens of interstellar objects pass through the inner solar system annually, within a few astronomical units of the Sun, close enough that they should be detectable if they produce comae or have reflective surfaces. But most remain undetected, passing through gaps in survey coverage, arriving when weather or technical problems prevent observation, or simply being too small and inactive to scatter enough light for current instruments to register their presence. The detection rate, currently 1 every few years, represents only the tip of a much larger population, the brightest and most active members of a swarm that floods through continuously but largely invisibly. Improving detection capabilities will increase the rate. Larger telescopes, more sensitive cameras, better image processing algorithms, more comprehensive sky coverage. All these advances will shift the threshold, will make visible objects currently too faint to detect, will catch visitors currently slipping through unnoticed. But even perfect detection would not capture everything, would not observe every object passing through. Some are simply too small, their surfaces too dark, their activity too weak to produce signals above the irreducible backgrounds of zodiacal light and instrumental noise. Only objects larger than perhaps 100 meters, and active or reflective enough to stand out against background sky brightness, are reliably detectable with technology planned for the next decade. Smaller objects, unless they pass extremely close to Earth, remain invisible. The population of interstellar visitors may be dominated by small bodies, by objects the size of houses or cars, outnumbering the larger, detectable objects by factors of millions. But these small visitors contribute little to the total mass, carry limited information about their birth systems, produce no measurable effects on the solar system they pass through. They exist in vast numbers, but they're observationally irrelevant, forever beyond human capacity to study individually. The time between detections encourages certain patterns in the scientific community. When an interstellar object appears, interest surges, telescope time is allocated, papers are written, conferences organise special sessions, the object becomes a focus of intense attention, a rare opportunity that justifies extraordinary efforts. Unusual collaborations, rapid publication of preliminary results that might be refined later when more data become available. But when the object fades, when observations end, the intensity dissipates. Researchers return to other projects, to long-term studies of solar system bodies, to investigations that do not depend on catching rare, fast-moving targets during brief windows. This pattern may change as detection rates increase. If Rubin Observatory delivers one interstellar object per month, if characterization becomes routine rather than exceptional, then the field might sustain continuous activity, permanent teams dedicated to interstellar object science rather than ad hoc collaborations forming around each detection. The infrastructure would be different, the workflows more standardized, the analysis pipelines automated for efficiency. What is currently a novelty might become a standard observational program, another category of target competing for telescope time alongside galaxies, exoplanets, and transient events. But for now, the silence persists. Months pass without new detections. The last interstellar object fades from view. Surveys continue operating, algorithms continue processing data, but the objects they find are all bound to the Sun, all members of the familiar populations that astronomy has studied for centuries. The wait for the next visitor extends, day by day, week by week, the duration unknown, the discovery date unpredictable, the properties of the next object uncertain until it arrives and observation begins. Somewhere in the interstellar medium, objects are approaching, not toward the Sun specifically, but moving through the galaxy on trajectories that will, by chance, carry them through the solar system's boundaries. Some are comets, volatile-rich bodies like 3I/Atlas, that will activate when solar heating sublimates their ices. Some are rocky, asteroid-like objects that will remain inert, detectable only through reflected light. Perhaps some are unusual, compositions or structures not represented in the 3 objects detected so far, outliers that will challenge assumptions and demand new explanations. These approaching objects are invisible, too distant for any current telescope to detect, too faint against the background stars. They will remain invisible until they enter the inner solar system, until automated surveys catch their motion, until preliminary orbit calculations flag them as unusual, as potentially hyperbolic, as worthy of targeted follow-up observation. The timeline is uncertain, measured in months or years, but the arrivals are inevitable, guaranteed by statistics, by the vast population of ejected planetesimals wandering the galaxy. When the next interstellar object appears, when telescopes turn toward it and spectra are collected and properties measured, comparisons will be made with Oumuamua, with Borisov, with 3I/Atlas. Does it fit the emerging patterns? Does it show elevated nitrogen, complex organics, anomalous spectral features, or does it diverge, presenting new puzzles, expanding the known range of interstellar object properties? Each new detection adds information, constrains the population, narrows uncertainties about what exists in the galaxy beyond this stellar system. But each detection also raises new questions, introduces new mysteries, reveals gaps in understanding. The process is not one of steady progress toward complete knowledge, but rather an expansion of awareness, a growing recognition of diversity and complexity, an accumulation of examples that show how much variation exists, how many outcomes planetary formation can produce. The goal of understanding galactic chemistry, of characterizing how matter organizes itself around stars throughout the Milky Way, recedes as it is approached, the questions multiplying faster than answers accumulate. And through all this, the objects themselves continue their journeys, indifferent to observation, unaware of the attention they briefly receive. They do not slow for study, do not linger for better measurements, do not return for follow-up observations. They pass through on their predetermined trajectories, visible only during brief intervals when they happen to be close enough and bright enough and correctly positioned for Earth-based telescopes to notice them. The rest of their existence, the millions or billions of years before detection, the millions or billions of years afterward, is spent in darkness, in the empty spaces between stars, where no light illuminates them, where no instrument can observe them, where they drift silently and alone. 3 I/Atlays has rejoined that darkness, its brief time in sunlight. Its few weeks of activity and observation are ending. The coma dissipates as sublimation slows and ceases. The dust grains disperse, scattered by radiation pressure, drifting into independent orbits that will carry them throughout the solar system and eventually into interstellar space. The nucleus, depleted of surface volatiles, develops a crust of refractory organics and silicate dust, a layer that insulates deeper ice from future heating, that ensures if 3 I/Atlas ever passes near another star, perhaps millions of years hence, the response will be weaker, the outgassing less vigorous, the spectral signatures fainter, and the object fades, recedes, disappears from human awareness. The telescopes that tracked it turn toward other targets. The researchers who studied it return to other projects. The data remain in archives, available for future analysis, for comparison with future detections, for refinement as new interpretation techniques are developed. But the object itself, the physical thing, the actual collection of ice and rock and organic molecules that briefly pass through the inner solar system, returns to anonymity, becomes once again just another invisible wanderer among the countless trillions that populate the galaxy, moving through darkness at 17 kilometers per second, carrying evidence of worlds that no human will ever visit, preserving chemistry from a star system that might not even exist anymore, completing a journey that began before Earth formed and will continue long after Earth is gone.